All right, I think we're live, everyone. So maybe make sure to let me know if the audio is good and stuff. We tested everything, but just it's always good to check. Okay, so what are we doing today? Well, I thought it would be cool, since the fall semester is about to start, to review types of problems that you should be comfortable with on day one of certain courses. So I know that, like, whenever I'm teaching a course, and I'm going through some examples, and I get to a part of an example where I rely on some information from previous courses, I see a lot of fear among my students. And so this is a little bit of my attempt to provide something out into the universe to maybe decrease that amount of fear. So at least you'll know what your professors are maybe expecting you to be good at once you start a course. Okay, so anyway, what courses are we going to look at? Well, I've prepared problems from Calculus 1, 2, 3. So what I mean is what you should be prepared for at the beginning of Calculus 1, 2, and 3. Linear algebra, differential equations, real analysis, and abstract algebra. Of course, I could add more things to this list, but I think this is maybe a good basic list to work with. Some classes, like an intro to proofs class, or sometimes called discrete math class, they don't really have any prerequisites. All you have to do to show up for those classes are have an open mind. I really think you could teach a course like that to someone without any math knowledge. Then something like linear algebra might have like similar prerequisites to like abstract algebra. Or more higher division courses like Abstract Algebra 2 or Real Analysis 2 or Complex Analysis, that's really just going to depend on your institution and exactly what you covered in the part ones of those classes. Okay, so anyway, that's my big spiel about what we're doing. Now, I'd like to point out that like all super chats for this live stream will be donated to the Randolph College Math Department. And so that's where I'm a faculty member at Randolph College in Central Virginia. And you might say, well, why would we do this? Well, our budget's not very big, but more importantly, I think if we had a little bit more resources, we could do some really cool things like have student events or do some outreach. And so in particular, me and the team member over here, Justin, who's off camera running the chat, we're thinking about doing like a big math contest for some local high school students that would maybe be simultaneously online. So there'd be like an online component for people that are far away and a component for people that are in, town. But, donations would help us do stuff like that. And then, I don't know, like I thought I'd do a backflip every $50. Is $50 the right amount to do a backflip? I don't know. Maybe I'll be doing only a few backflips. Maybe I'll be doing many, many, many backflips. But I think I'm up for the challenge. Okay, so anyway, now that we've got this going on, let's maybe go ahead and get started. So we'll start with Calculus 1. And, I'll just say the course. But maybe one more time I'll reiterate what we're going for is what you should be prepared for on day one of the course. Okay, so let's see. I think we've got, can you put Calculus 1 on the screen? So Calculus 1. Okay, so I would say like some important basic skills to have before we look at examples are basic symbolic manipulation. So
the audio is kind of bad.
Cool.
Can they at least hear you? I'll just say bad how. Here, I'm scrolling. Somebody said good enough. Somebody said sounds worse compared to your videos. Doesn't sound right.
Yeah, I mean the system is different than my videos.
Audio's fine. Well, I'm getting mixed signals.
You guys are really difficult.
Yeah, like background noise. Audio's good. Mic is fuzzy. Like every other comment.
Okay, so
just do it.
Basic symbolic manipulation, that's going to be an important skill. Knowing like domains of functions and in particular what kind of things
Somebody donated $50.
Restrict the domains. Okay, that means we have to do a backflip. Maybe graphs of common functions. Could you need to know more? Yeah, probably, but I think this is probably a good place to start, and knowing this type of stuff will put you in a good place to succeed in Calculus 1. Okay, so now let's look at some types of examples that you should be, really, really comfortable with. So let's maybe start with something like this. We'll have a quadratic inequality. So x squared plus 9 is less than 6x. Okay, so anytime you've got a higher degree polynomial, what you probably want to do is set it up so you have 0 on one side of the equation or inequality. So in this case, it would be x squared minus 6x plus 9 is less than 0. Then hopefully we can factor this. If we can't factor this, then there's more to do. But in fact, we can factor this, right? Yeah, we can factor this like x minus 3 squared is less than 0. But there's clearly a problem here because this is a perfect square. But perfect squares are always bigger than or equal to 0. So that tells us we in fact have no solution to this inequality. So in other words, like the empty set is our solution. Okay, so now that we have our basic, very, very first basic example looked at, let's maybe look at the graph of a function. So you do lots of graphs of functions in Calculus 1, but in a pre-calculus class you often look at some simple ways of graphing functions. So let's maybe see a function that you might graph from a pre-calculus class. So let's say you have the function f of x. Let's say it's x squared times x minus 2 squared times x plus 2. Okay, so first of all, what we see is that this is a 5th degree polynomial. And in fact, if we were to multiply this out, we would see it would be x to the 5th power plus more. And so the important thing here is that we have a positive coefficient in front of the x to the 5th. And so what that means is that its end behavior as x goes to minus infinity is minus infinity. And then its end behavior as x goes to plus infinity is plus infinity. So in the calculus world, these are thought of as limits, but in a pre-calculus class, which I generally teach a pre-calculus class every year, you say the word end behavior instead of limit. Okay, so that gives us a good starting point for the graph. And then we can also look at the zeros of this polynomial to maybe fill in what it looks like in the middle, if you will. So let's notice we've got a 0 at x equals 0. That's pretty clear because we have this x squared out front. We have a 0 at x equals minus 2. Let's maybe put that back here. And then we have a 0 at x equals 2. Let's put that up here. And now we need to draw a graph that has these properties. So it goes through these 1, 2, 3 points, and then it has this end behavior. Then we will also use the fact that these are even zeros, so zeros of even degree, which means that the graph turns around at these points. Okay, so let's see how we could maybe do this. So let's see. It's going to go straight through x equals minus 2 because this is of odd degree. And then it'll turn around here at x equals 0. And then also turn around here at x equals 2 and then go up to infinity. So maybe the picture would look something like this. Okay, so now moving on, let's look at something which comes into use every once in a while in a Calculus 1 class, but it's at least useful to be ready for, and that is completely factoring larger polynomials using the rational root theorem. So let's completely factor the following cubic polynomial. So let's say we've got x cubed and then plus 3x squared and then plus 4x plus 12. Okay, so the rational root theorem will tell us the possible rational roots, And those possible rational roots are the factors of the constant term divided by the factors of the highest degree term, with a plus or minus there. So here we've got just 1 in front of this, so that's helpful. We only need the factors of 12. So those will be plus minus 12, plus minus 6, plus minus 4, plus minus 3, plus minus 2, and plus minus 1. Another good thing to think about is probably the problem is not trying to hurt you too much, and so likely it won't be any of these larger numbers, just given that most textbook problems kind of have some easiness built in. So let's check some of these. Notice we don't have any positive roots. It's pretty easy to see that we don't have any positive roots because the coefficients of all of these numbers are positive, or all of these powers of x are positive. So if we plug a positive number in there, that'll clearly be positive. So that means we only have possible negative roots. So let's maybe scrub out the fact that this could be positive 12, positive 6, positive 4, positive 3, positive 2, or positive 1, and let's check the others. So f of minus 1, so that's going to be minus 1 plus 3 minus 4 plus 12. That's clearly not equal to 0. And so let's check f of minus 2. So f of minus 2 will be negative 8. And then we'll have, let's see, plus 12. So that's from this. And then minus another 8. And then plus 12. But again, that's clearly not equal to 0. Okay, so let's look at maybe f of minus 3. So that's going to be negative 27 from this, and then plus a 27 from this, and then minus 12 from here, and then plus 12 from here. So that is 0. So that tells us that x equals minus 3 is a root. But that means that f of x can be written as x plus 3 times some sort of quadratic polynomial. And then we can really guess and check the coefficients of that quadratic polynomial. So notice that we need a coefficient of 1 in front of the x squared. We need a coefficient of 1 in front of the x squared because we've got a coefficient of 1 in front of the x cubed here. I guess maybe I should say that at this point you could use polynomial long division, but I think that's kind of overkill. We will maybe need to use that for partial fraction decomposition later, but we'll hold off on that right now. Okay, so anyway, then we'll need a plus 4 here. And that'll give us the 12. And then let's see what we need in the middle. Well, we need a 4x, but notice that we get a 4x just from this x times 4. And then that looks like we don't need a linear term. And clearly we also don't need a quadratic term because we get a 3x just from what's there. So what we really have is plus 0 times x, but let's just move this in. So it's x squared plus 4. So if you wanted to look at all roots, maybe real and complex, we would have negative 3 and then plus minus 2i, which we get from setting this equal to 0. Okay, so this is kind of a problem which you wouldn't necessarily see something exactly like this in Calculus 1, but it's useful to have these sorts of skills. In fact, it's a little bit of a bummer that Calculus 1 has some really beautiful ideas that can be explained pretty easily, like the slope of the tangent line, area under the curve, instantaneous change, but it's also important to have these symbolic manipulation skills, which are not super beautiful or motivating in order to succeed in most courses like this. Okay, so anyway, that's just kind of a neither here nor there type of thing. All right, let's look at a couple more. So let's solve the following exponential equation. So let's say we have 3 to the x. Any word on the sound? Is it fine?
I haven't heard any complaints, so it's probably all right.
So plus 25 times 3 to the minus x. Are people still there?
Yeah.
Okay.
You got plenty.
Equals 10. And you're keeping a running total, so we know when I have to do a backflip? Mm-hmm. Okay. Okay, so let's say we want to solve something like this. Well, I think maybe the first thing to notice is that we've got 3 to the x here, 3 to the minus x, but 3 to the minus x is the same thing as 1 over 3 to the x. So that motivates me to do a change of variables. Maybe I would set t equal to 3 to the x, and that means my equation is t plus 25t to the minus 1 equals 10. Then I can take this thing and multiply by t, giving me t squared plus 25 equals 10t, but that's a quadratic equation for t. We have t squared minus 10t plus 25 equals 0, which means we can factor this as t minus 5, quantity squared equals 0, which tells us that t equals 5. But t is equal to 3 to the x, so that really means that 3 to the x equals 5, which means x equals the log base 3 of 5. If we wanted to extract that from the exponent. Okay, good. Now let's maybe do one trigonometric type equation, and then we'll move on to our next course. Or actually, maybe before we move on to the next course, we'll see if there's like any types of problems that you guys have suggestions to do. We'll do that at the end of each class that we're covering. Okay, so anyway, let's solve this. Let's solve sine of x plus the square root of 3 times cos x equals 1. Okay, so maybe the first thing that I'd like to do here is solve for sine of x. So let's see, sine of x is equal to the square root of, well, let's 1 minus the square root of 3 times cosine of x. So something like that. And now we can square both sides. That'll give us sine squared x equals 1 plus 2 root 3 cosine x. That should be a minus. And then plus 3 times cosine squared of x. But we still have cosines and sines in here, but luckily we have the Pythagorean identity. And the existence of this Pythagorean identity is actually all of the motivation to square this in the first place. We know sine squared is 1 minus cosine squared. So that immediately allows us to cancel this 1 from both sides of the equation, and then we can move some things around, and we'll see that we get 4 times cosine squared of x minus 2 times the square root of 3 times cosine of x equals 0. Now we can factor a 2 cos x out of this, leaving us with 2 times cosine of x minus the square root of 3. Which tells us that cosine of x equals 0, or cosine of x equals the square root of 3 over 2. So cosine of x equals 0 at half integer multiples of pi over 2. So, sorry, half integer multiples of pi. So this is going to be x equals pi over 2 plus 2n, well, actually plus n pi. In pi. And then cosine of x equals the square root of 3 over 2 at other places that I don't remember at the moment. Is it pi over 6 or pi over 3?
Pi over 6.
Good. So x equals pi over 6, and then like all shifts of pi over 6 by, appropriate amounts. Okay, cool. So now, are there any questions or anything that you guys want to go over before we move on to stuff to be ready for Calculus 2? Nothing? Cool.
Nothing yet. Somebody says we should have something on the board to denote that $50 is a backflip.
Yeah, you could. Did you pin a comment or something?
The comment was about the donations, but I could pin something like that. Can you pin 2 comments? I don't think so.
You could include it in the pinned comment.
Can you edit the comment? Doesn't look like it. Just have remove and unpin.
Well, you could like write a new comment that has that and then...
I can make it on the graphic.
Okay. Anyway, calculus 2. Yeah, maybe make the graphic go by every once in a while. Okay, so calculus 2. So I would say like some important things to be very familiar with at the beginning of calculus 2 are the derivative rules and derivatives of basic functions. So you'll need to recall the product rule, the quotient rule, the chain rule, and then, like I said, derivatives of basic functions. And then you'll also need to be familiar with basic integration, but I think most of the basic integration that this will all boil down to is being good at U substitution. So U substitution is generally done at the end of a Calculus 1 class when everyone's like kind of tired and it doesn't really sink in. But having a very strong like skill set of doing integrals with U substitution will help a lot starting Calculus 2 because, you know, generally in a Calculus 2 or an integral calculus class, there's not a huge amount of time to review basic U substitution techniques as you generally move on to like other techniques. Okay, so let's look at some examples based off of this type of stuff. Okay, so maybe let's like find the derivative of the following function. So let's say f of x equals x times the natural log of x times the sine of x. So here we'll have to use the product rule. Really the product rule 3 times. So here we'll have f prime of x will be equal to, let's see, we need to take the derivative of each of these one at a time. So we've got x, we've got natural log of x, and we have sine of x. So taking the derivative of x while holding the others constant will give us natural log of x times sine x, given that the derivative of x is 1. Then plus, for our next one, we'll take the derivative of natural log of x while holding these two constant. So that'll be x times 1 over x times sine of x. Here I use the fact that the derivative of natural log was 1 over x. And then next, we'll take the derivative of sine x while holding these two constant. That'll go this x ln x cos x. Okay, so that's the kind of thing that we get in the end. Obviously, that can be simplified a little bit to the natural log of x times, let's see, sine of x plus x cos x, and then plus sine of x. So what I did here is I just factored this natural log out of these two terms, keeping in mind that one's attached to a sine, whereas the other is attached to x times cosine of x. Okay, so now let's find equation of tangent line of this function at x equals 0, of blah 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 at x equals 0. So let's see what function we're talking about. I'll call it g of x, and let's say it's x plus the inverse tangent of x. So, I mean, mostly the reason to do this one is to just recall what the derivative of the inverse tangent is. The derivative of the inverse tangent and the antiderivative of the associated function show up like more often than you might think in an integral calculus class. Okay, so anyway, we have g prime of x equals 1 plus derivative of arctan is 1 over 1 plus x squared. So there's our derivative. But to find an equation of a line, we need a point and we need a slope. So the point we can get just by plugging 0 into our original function. So that'll be 0, 0. And that's because arctan of 0 is 0. Remember, arctan is the inverse tangent. It's like asking a question, when is the tangent equal to 0? Well, that occurs at 0. It occurs other places too, but remember the arctan only has the arctan's only inverting part of the tangent. Okay, so now let's plug x equals 0 into the derivative to give us our slope. And note that we get 1 plus 1 over 1 plus 0, so we get 2. Okay, so we've got a point and a slope. That allows us to find the equation of the line pretty easily. It's y equals 2x. Here I could really use the point slope form, so y minus the y part of the point equals slope times x minus the x part of the point, but I think this one collapses pretty quickly. Okay, so let's do another one. Okay, so let's say our next example is to find the nth derivative of this function, which I'll call f of x, which is x times e to the x. So, I mean, depending on how fancy your calculus class was, there are different ways to approach this. Sometimes you might just do a couple of examples and then guess the solution, and that's good enough. Other times you might want to prove this with induction. Maybe we'll sketch an inductive proof, but we won't go ham into that because we're going to review induction later. Okay, so let's just make some lists. So the derivative is equal to, let's see, that'll be x e to the x plus e to the x. That's using the product rule. We have the product of two functions, x and e to the x. And then the second derivative, well, that's going to be equal to, well, we can use the sum rule for the derivative. We have x e to the x, and then we have e to the x. But we just took the derivative of x e to the x, and it spread out into these two terms. So that means this orange underlined thing will also spread out into those same two terms. X e to the x plus e to the x, and then the derivative of e to the x is e to the x. Well, now we can combine some things together and we get x e to the x plus 2 e to the x. And now I think you can see what's happening. We've got a first derivative here and one copy of e to the x. Here we have a second derivative. We have two copies of e to the x. You can pretty easily check that the third derivative here will be x e to the x plus 3 times e to the x. That's going to be 3 copies of e to the x. So you might finish this thing off by saying claim the nth derivative, which I might denote like this, is equal to x e to the x plus n times e to the x. And then how would you prove this? Well, like I said, depending on the expectations of the class, you may not really have to prove something like this because it's like a class at a low level. But you could do it maybe with induction. You could assume that it was true for k, and then you could take the derivative with respect to k of the kth derivative. So the derivative of the kth derivative is the k plus first derivative, but that's the derivative with respect to x of x e to the x plus k times e to the x by the induction hypothesis. But then just by using derivative rules here, this is very clearly x e to the x plus k plus 1 e to the x, which is all that's really required to finish off this inductive argument. It's really too bad that induction isn't taught sooner, because you could do really nice things like this in earlier classes, and I don't think it's really that complicated of a topic, but that's kind of neither here nor there. Okay, let's look at some integral examples now. So like I said before, in the US at least, integrals are taught at the end of a Calculus 1 class, when everyone's getting tired. So no one, well, not no one, but I found that often it's easy to not internalize all of the integration techniques, even though Calculus 2 is all about integration, and it's thought of as the hardest calculus class because it builds off this stuff that you learn at the end of Calculus 1 when you're tired. Okay, so anyway, let's look at this integral. Let's say we have cos theta minus 1 times cos squared theta minus 2 times cosine of cubed theta. No, sorry, cosine of theta all cubed, and then times sine of theta d theta. Okay, so you look at this and you see, oh, it's super complicated, right? But I just finished Calculus 1. I don't know a ton of integration techniques. So you might say, well, what do I know how to do? I know how to do U substitution. And the pillars of knowing when to use U substitution are to look for a function inside an integral whose derivative is also inside the integral. And that's exactly the situation that we have right here. Notice this function cosine is all over the inside of this integral. And its derivative is also in the integral, and the derivative is like only in one place. I guess that's kind of an important part as well. So that motivates us to make the following substitution. Let's set u equal to cos theta. Notice that means du is equal to minus sine theta d theta. It's like the differential one form, if you will. But that tells us that minus du is sine theta d theta. So we've got this substitution for u, and now we have this substitution for du. Okay, so notice that we can take this sine theta d theta and replace it with minus du, given a purple box right underneath, and then we can replace each of these with u. So this is u squared, and this is going to be minus 2u. So let's see what that leaves us with. Now we have the integral of u minus 1 times u squared minus 2u all cubed, and then times minus du. I don't know. Let's maybe put a minus sign out front, and then we'll put a du here. But there are a couple ways to work with this. Notice we could cube this guy out right here. Cube this guy out right here, and then maybe multiply it with a u minus 1, then we've got a big polynomial. But if you look at this carefully, you can see that this u squared minus 2u, its derivative is almost exactly u minus 1. It's just off by a constant. So that motivates us to do another change of variables. So now let's set, so we need like another variable here. Let's maybe use t. Let's set t equal to u squared minus 2u. That means dt is equal to 2u minus 2 du. But notice that's 2 times u minus 1 du. Okay, cool. But notice I have u minus 1 du, not 2u minus 1 du. So that motivates me to solve and get u minus 1 du equals half dt. Great. And so these are like my dt earmuffs. So this is minus half, sorry, this is just half dt, and then this just turns into t. Okay, so that's looking good. Now I can bring this minus, or this half out, becomes a minus half because of this minus sign right here. And then I have the integral of t cubed dt. But we can just use the power rule on that, no problem. So the power rule is going to give us minus 1 over 8 t to the 4th. So we have something like that, and then I guess like plus a constant. And then let's see, that's going to be minus an 8th, and then t can be replaced with this thing right here, but each u in this replacement can be replaced with cosine. So we really have cosine squared theta, and then let's see, minus 2 times cos theta. That's all to the 4th plus a constant. Okay, so there's a nice u substitution type problem. And now let's see what we have next. Okay, so for our next example, let's look at the integral from 0 to 1 of x times the square root of 1 minus x squared dx. So this is another U substitution type problem, which may not seem like super interesting after the one we just did, but what I'd like to do is compare and contrast this with another problem that looks pretty similar but doesn't quite use U substitution. Okay, so anyway, one of the main pillars of doing substitution to solve integrals is looking for a function inside the integral, generally composed within another function whose derivative is also in the integral. We have that here. 1 minus x squared is composed within the square root. Its derivative is outside. So let's take u and set it equal to 1 minus x squared. That means du might be equal to minus 2x dx, which tells us that x dx is minus 1/2 du. My color coding is not great. I apologize. Okay, so we have that type of situation. Now, let's see, inside of our integral, this is going to become u, and then I have my earmuffs here that turn into, let's see, minus 1/2 du. So that means my whole integral becomes minus 1/2. I can bring that constant out. I have the integral of just u du. Then you might say, well, what about the bounds of integration? So I've noticed that like most, well, I don't want to say most, but it's pretty common for students just to like maybe not worry about the bounds of integration right here and then substitute back to the original integral at the end. But I think it's maybe a better strategy to change the bounds of integration. I say this is a better strategy because it generalizes to integrals with more than one variable a little bit better than it would otherwise. Okay, so anyway, let's see what we have going on here. Let's recall that this is a lower x bound of integration, x equals 0, an upper x bound of integration, and we need to change these into u bounds of integration. Okay, but we can do that with our rule right here, our substitution rule, which is great. So notice if x equals 0, that implies that u is equal to 1 minus 0. Pretty sure that's 1. And then when x equals 1, which is that upper bound, that tells us that u is equal to 1 minus 1, that is 0. So that changes our bounds of integration to 1 to 0.
You need your square root on your u.
Thank you. That's the first mistake I've ever made in any video that I've ever recorded. Isn't that amazing? It took that long. I've almost got 1,500 videos. That's the first mistake I've ever made. Okay, so anyway, good. We're good now. Now, generally what I do in videos is I just scrub this minus sign out and flip the bounds of integration, but let's leave that step in here, and I'll take this minus sign and use it to swap the bounds of integration. So this is going to be 1/2 the integral from 0 to 1 of u to the 1/2 du. So from here I can use the power rule. So I increase the exponent by 1 and divide by the new exponent. I've got 1/2 that comes from here. Increasing the exponent by 1 is 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3. U to the 3/2 evaluated from 0 to 1. Evaluating at 0 gives me 0, evaluating at 1 gives me 1, so I really just get 1/2 times 2/3, which is likely 1/3. Okay, so let's do one that looks pretty similar, and is potentially simpler, but is often like missed more by students because it requires like a little bit more fiddling. So let's look at the integral from 0 to 1 of x times the square root of 1 minus x. So no squared there. So this this is like not quite the same type of u substitution, and that is because my composed function here, 1 minus x, its derivative is not anywhere else, right? Its derivative will not gobble up this x on the outside like we had here. So we've got to use some sort of other strategy. And this other strategy is sometimes called like back substitution or rationalizing substitution or something. There are like a couple of different things that you can do, but I think maybe the best bet is to let u equal 1 minus x. But then instead of finding du and trying to build it into this integral, what we'll do instead is solve for x. Notice that means x is 1 minus u. And then we can calculate dx. So that means dx is minus du. Okay, but that's everything we need to change this integral. So notice this x can be replaced with 1 minus u. This 1 minus x can be replaced with u to the half. It's in the square root. And then this dx can be replaced with minus du. Okay, so that's going to leave me with the integral from 1 to 0. I'll change the bounds of integration just like I did over here, but I won't.
$100 donation.
But I won't labor that. Wow, thank you very much. Okay, so, but I won't labor that change of variable, or that change of, well, I'm all discombobulated now. I won't labor that change of bounds of integration. It's the same thing as over here. We're just lucky that 0 squared is 0 and 1 squared is 1, so the same kind of thing happens. Okay, so now that we have 1 minus u to the half du, I brought that minus sign out. Let's take this minus sign and use it to flip those bounds of integration back. Okay, then we probably want to multiply this out. The integral from 0 to 1 of u to the half minus u to the 3 halves du. Okay, now we can just use the power rule on each of those. This will be 2/3 u to the 3 halves minus 2/5 u to the 5 halves, evaluated from 0 to 1. Is that right? That seems right. Okay, then plug 1 in, and we'll get 2/3 minus 2/5. I think that's 0/5. Just kidding. So let's see. That's going to be 10 over 15 minus 6 over 15. So that's going to be 4 over 15. Great. Okay, good. We did one. Okay, let's do another one.
We've been live for 50 minutes on this.
Whoa! Okay, so let's look at this. The integral of sine squared theta cos cubed theta d theta. Okay, so again, you are just a finishing Calculus 1 student, you're just starting Calculus 2, you only know about u substitution, but I look at this and I see two functions here that are composed within other functions, and their derivatives are like not really to be seen in the kind of easiest way. But if I remember something about Pythagorean identities or trig identities, I know that I can split this into cosine squared theta times cosine theta, and then further split this into 1 minus sine squared theta. And then that motivates a pretty nice substitution. So that leaves me with sine squared theta minus sine to the 4th theta times cos theta d theta. Okay, so let's see what happened there. This sine squared multiplied onto this 1 and this other sine squared, and then this cosine just came down. Okay, but now I've got sine composed within this polynomial equation, and then the derivative of sine is outside, so we have the setup. So let's let u equal sine theta. That makes du equal cos theta d theta, just as we need. And then this turns into a polynomial. So this is u squared minus u to the 4th du. So that's a 3rd u cubed minus a 5th u to the 5th plus a constant. And then you can plug sine theta into each of those. So you get sine cubed there and sine to the 5th there, but I won't write that down. Okay, let's maybe do one more. And then we'll move on to our next course. Or maybe we'll ask. You guys...
I think we've seen the most requests for linear algebra so far.
For what to know before linear algebra? I don't have much for that. Because what to know, there's not a ton to know before linear algebra because it's like pretty self-contained. I hate to tell you that. We'll go over a little bit. We'll go over some linear algebra when we review what's important for differential equations, because there's a lot of linear algebra you need for differential equations, but linear algebra is pretty self-contained, so it's hard to... Anyway, everyone's gone.
You got 180 people, not everybody's gone.
Unsubscribe. Okay. Dx over x square root of 1 minus natural log of x quantity squared. Okay. So this one looks pretty gnarly, but given how gnarly it looks, especially kind of armed with the knowledge that it's fairly easy to write down an integral that has no like elementary antiderivative, or a function that has no elementary antiderivative, and then you're given this in a certain setting where you're trying to find the antiderivative, means there must be a trick. And the trick is going to be another substitution. You might say, well, oh look, I've got this 1 minus natural log squared inside of a radical. Maybe that should be my choice for my substitution, but if I take the derivative of that, it's a big mess. And it doesn't like gobble up everything on the outside. It provides me with like kind of too much. Then you see that natural log itself is composed within two functions, in this square function and in the square root. So that maybe motivates us to do the substitution u equal natural log of x, which means du is 1 over x dx, or maybe we would write that as dx over x. And then looking at this, we see that we have exactly that. We have this dx over x here, that's my du, and then this gives me u. So that allows me to rewrite this as du over the square root of 1 minus u squared. And then you're bummed again, because this looks like a gnarly integral, right? I would take... If I tried a substitution, 1 minus u squared, notice my derivative is nowhere to be seen, so there must be another way to do it. But this is where you remember there are these class of functions, these inverse trig functions, that have really bizarre derivatives and thus give you really bizarre antiderivative rules, and that's what you'll use here. So unfortunately, this is one where you just say, okay, I know the function whose derivative is this, and it's the inverse sine function. So arc sine of u plus a constant. I just made a video about why there's an arc and arc sine, by the way. Okay, so then we need to substitute back in. So this is going to be the arc sine of the natural log of x plus a constant. Okay, so we've got something like that. Okay, sweet. So now let's move. Are there any things that we want to go over?
What class are we going to next?
Calculus 3.
Alright.
There's less to say about Calculus 3 than there is about Calculus 2, because Calculus 3 is again like a little bit more self-contained. Calculus 2, although it's a fun class and it has really interesting information in it, there's one thing that's like a little bit unfortunate about it, and that it is very not self-contained. And so often it really behooves you to like pre-prepare some tricks from Calculus 1 to remember in Calculus 2, more so than other classes. Okay, so anyway.
Somebody asked for series test.
Yeah, we'll be going over that when we go over like prereqs for differential equations. We'll look at some series. Okay. Okay. So some important things for Calculus 3. So I was like really just kind of grasping here when I thought about this list. So I'm going to put here being solid at Calculus 1 and 2 information. So in other words, like knowing your derivative rules really well, knowing your integration techniques pretty well, although the gnarly integration techniques from Calculus 2 don't show up a ton in Calculus 3. But just kind of generally being solid here is good. Maybe remind yourself about the fundamental theorem of calculus. So I'll put that here. Understand the fundamental theorem of calculus. So let's recall that says that if you take the integral from a to b of the derivative, well, let's write it like this maybe. The derivative of capital F of x dx, you end up with capital F evaluated at b minus capital F evaluated at a. So notice here we've got a derivative inside of a single integral. And what it gave us is what I like to call a zeroth integral, which is really just evaluation of a function at two endpoints. So somehow this derivative and this integral annihilated each other and just gave us evaluation of the function at the boundary. So I say understand the fundamental theorem of calculus because this is working towards some things you learned at the very end of this class, like Green's theorem, Stokes' theorem, the divergence theorem, which put generalizations of this idea. There's this idea of like a type of integral being simplified by a type of derivative. Okay, so next, I'm going to put vectors here. Even though vectors are covered in Calculus 3 without any kind of requirement to know them beforehand, what you'll notice if you're a pure math student that hasn't taken anything else is often your classmates who have been in physics classes are really good at the first part of Calculus 3 because they worked with vectors in their physics classes, whereas you maybe haven't seen them. So it might be nice to kind of look about something about vector arithmetic. And then maybe I'll just say like parametric equations, so parametric equations, and then polar coordinates. So this is stuff that is gone over generally in like pre-calculus type classes, so it's probably been a while, but it shows up really in an important way in a Calculus 3 type class. Sometimes you cover that again in Calculus 2, but not all the time. Okay, so I'm not really going to do anything with these first two dots, any types of examples for these first two dots, because there's not really much to be said. These are like kind of soft examples or maybe suggestions. Maybe we'll like look at some examples with vectors, parametric equations, and polar coordinates. Okay, so let's maybe do this one. Let's find a unit vector perpendicular to this vector, maybe I'll call it v, which is the vector 1, -3. I don't know why I look at my notes. We could obviously do 1, 3. That would be fine. Okay, so notice I've got a two-dimensional vector here, so that means I should be looking for a two-dimensional vector that's perpendicular to this. So just maybe we can make a picture of what's going on here. So our vector v, it's like horizontal component is 1, its vertical component is -3. So 1, 1, 2, 3. So the vector v looks something like that. But notice it's like orthogonal complement, if you will, is an entire line. So this whole line is perpendicular to it. But we're just looking for a unit vector perpendicular to this v. That unit vector could really be pointing in any direction. It could be pointing that direction or that direction. So really there are two choices for unit vectors, but we'll just get one of them and call it good. Okay, so let's maybe recall that w, which I'll call AB, is perpendicular to v if and only if v dot w equals 0. So that's like not really the definition of perpendicular when you're talking about vectors in 3 space, but that becomes the definition of orthogonality when you're talking about like vector spaces. The dot product or the inner product being equal to 0. Okay, well, we've got this like vector given for v, this like arbitrary vector for w, so maybe we could set up some sort of system of equations. So we've got 0 equals v dot w, but we need to dot product those two vectors. Let's recall that that is just like overlapping their components, multiplying, and then summing. So that's going to give us 1 times a plus negative 3 times b. So that's 1 times a, negative 3 times b, and then you add them. So this is going to be a minus 3b. We want that to be equal to 0. Well, let's note that that means that a equals 3b by arithmetic. And then one of those is a free variable, but we expect one of them to be a free variable given that, I said that this entire line is in the, orthogonal complement of this thing. So maybe we could take b equal to 1 for simplicity, and we'll have w equals 3, 1. But let's notice that's not a unit vector. It is orthogonal to our v, but not a unit vector. So let's make into a unit vector. So we can do that by dividing or doing a scalar multiple of 1 over the magnitude of this vector. So we'll define u, our kind of final answer for our unit vector, to be 1 over the magnitude of w times w, where that's scalar multiplication. So let's see, that's going to be 1 over, remember the magnitude is going to be the square root of 3 squared plus 1 squared, that's going to be the square root of 10. We just use the Pythagorean theorem to find that like magnitude, and then times our vector, which was 1 minus 3. So I don't know, maybe that's like the final answer that you would write down. Oh, sorry, not 1 minus 3, 3, 1. 1 minus 3 was my original vector. So maybe you would bring that in there. So that's going to be 3 over root 10, 1 over root 10. That would be our unit vector perpendicular to our given vector. And just like a heads up, that's going to be the one pointing in this direction. Good. If we had like taken b to be equal to minus 1 right here, it would have been pointing in the other direction, just kind of FYI. Okay, so let's look at another example. So this is like in the realm of polar coordinates. So determine the following in rectangular coordinates. So let's say we've got this equation r equals cosine theta. So let's say that's our equation. And then before we get started with this example, let's recall our little translation tool for rectangular to polar coordinates and back. So we have x equals r cosine theta, y equals r sine theta. So that's our translation from rectangular to polar coordinates. And then from this, we can easily see that x squared plus y squared is r squared cosine squared plus r squared sine squared, which is r squared. Okay, and then there are some more based off of this, like I think tangent theta is y over x or something. But this is all we'll really need in order to change this into rectangular coordinates. So we've got an r, we've got a cosine theta on both sides of an equation. But really looking at these three equations, I need to manipulate this a little bit to use these three equations to do our translation. And I think maybe the most obvious thing to do is to start by multiplying by r. Beer. So let's see, that's going to give us r squared equals r cos theta. Now that we've got that, we can use these translation rules. That gives us x squared plus y squared equals x. Then, well, okay, that's a curve in rectangular coordinates, but what curve is it? Well, we could maybe like complete the square and figure that out. So x squared minus x plus y squared equals, well, 0 at the moment. So I just moved the x over. So now we're going to multiply by something here to complete the square, or sorry, add something here. So the general rule for completing the square is you take half of the linear coefficient and you square it. So half of 1 is half, squared is quarter. So this is going to be plus quarter. And that makes this thing factor like x minus half squared plus y squared equals quarter, but I'll write that as half squared, just so that we can see that is a circle with a center of half, 0, and a radius of half. So let's see, if we put a half there, we put a 1 there, then this is a circle like this. This is a terrible circle. Yahtzee. Okay, so let's look at another one, so something related to parametric equations. Okay, so let's find dy dx if x equals y equals. So let's say x is t squared minus 4t, and let's say y is 2t cubed minus 6t. So let's say we have that like kind of situation going on here. So let's just recall a fact. So maybe I won't go into like proving this fact. It's done in like the calculus 2 section where you're doing polar coordinates and parametric equations. But the fact goes like this: dy by dx equals dy by dt over dx by dt. I know this seems like not great because it looks like you're just like canceling out the fraction, but that's not really what's going on here. You prove this like with the chain rule and stuff like that. So, but it just turns out that this is like kind of the nice way to do it. So anyway, let's take these derivatives with respect to t. That shouldn't be too hard. We get 6t minus 6 here using the power rule, and here we get 2t minus 4. So we end up with something like that. We can factor a 2 out of the numerator and the denominator, end up with 3t minus 3 over t minus 2. So that looks good. Now notice that this has a horizontal tangent at t equals 1. Why do I know that? I know that because that makes my derivative equal to 0 because my numerator is equal to 0 while my derivative is not equal to 0. So t equals 1 means what coordinate are we at in the xy plane? Well, we can plug that t equal 1 into our original setup, so that's going to be minus 3, minus 4. And then we have a vertical tangent at t equals 2. How do I know that? Because that makes the denominator equal to 0 while the numerator is not equal to 0. You might say, well, what happens if they're both equal to 0? You have to do some like careful stuff with limits. Okay, so let's see. That's going to give us the coordinate of 4 minus 8 is negative 4, I think.
You're saying you need the t squared in your numerator.
Oh, yeah. Well, I can fix that. Sorry, not sorry. Now that I've like committed to doing this arithmetic in my head, I can't like go back and I'll make the arithmetic. It'll be bad. All right, what do we get if we plug t equals 2 in here? We get 2 times 4, which is 8, minus 12, which is negative 4. We get negative 4. Maybe it's that. Okay. So let's do one more. And that would be like maybe finding arc length. So let's find the arc length of the curve defined as follows. Let's say x is equal to cosine cubed theta, y is equal to sine cubed theta, and let's say theta runs from 0 to 2 pi. Okay, nice. So let's see. Let's recall that the arc length is given by this formula. So it's going to be the integral from a to b, and then the square root of dx d theta squared plus dy d theta squared. There's like a really nice way to do this where you like take a curve and break it into line segments and then find the length of those line segments using the Pythagorean theorem, and then take a limit and stuff like that. You use the mean value. It's like really beautiful how you develop this formula. Okay, we did it in the like very, very long Calculus 2 live stream back in the day. So this is going to be the integral from 0 to 2 pi, the square root of, so the derivative with respect to theta of cosine cubed, so that's going to be 3 cos squared theta times sine theta, and then we square that whole thing. You might say, oh no, you made a mistake, the derivative of cosine is negative sine, but we're squaring this bad boy, so it doesn't matter, the minus sign disappears. And then here we're going to have 3 sine squared theta cos theta, that whole thing squared. And then I don't have room for my d theta, so we've got something like that. Now, let's see what we can factor out of this. Hopefully a lot, so that we can have something nice just in the radical. So let's see. This is going to be the integral from 0 to 2 pi of the square root of, let's see. Let's do the simplification right here. So this is going to be 9 cos 4 theta sine squared theta. And this is going to be 9 sine squared theta. No, sine 4 theta cos squared theta. So we can take a 9 cosine squared sine squared out. So 9 cos squared theta sine squared theta. And then what are we left with? We're left with cosine squared plus sine squared, Yahtzee. Cosine squared plus sine squared. That's, you know, it's a normal thing people say, so don't worry about it. Okay, so let's see. Cosine squared plus sine squared is 1. Then this is a perfect square, so we can just like have it annihilate the square root. So this gives us the integral from 0 to 2 pi of 9 times cosine theta times sine theta. Then I just realized, you know, there's some mistake in here because I'm about to get 0. But clearly the length of this is not 0. So does anyone in there know what's going on here? Can we just wait? I know there's a delay, which makes the waiting like awkward.
Awkward, yeah.
Yeah, I could just like tell jokes.
Start doing stand-up.
But I don't. So the other day, Justin asked me how to do something. Didn't even Google it first.
What's the deal with the airline?
I thought he was, you know, he's supposed to be some young kid. Can't even type it into Google.
Yahtzee counter 3. That's what people are saying.
I don't know how to do things.
Oh, there's a bot. I gotta ban the bot.
Okay, what do we know about this problem? Why am I about to get 0 for this problem, and I know I should not be getting 0?
I gotta moderate this bot. Somebody says, you forgot absolute value. Absolute value. They're all saying absolute value.
Where's the absolute value? Oh, yeah. Thank you very much. Absolute value, absolute value. So when is that positive? So that means I can split this into the part where it's positive and the part where it's negative. So this is going to be like the 4 times the...
They're also saying 3, not 9. Because the square root.
Thank you. So this is going to be 4 times the integral from 0 to pi over 2 of 3 times cos theta sine theta d theta. I think you get to multiply by 4 because that's splits it into, because of the like periodicity of this. I mean, now we're really playing it fast and loose. So this is 12, the integral from 0 to pi over 2 of sine theta, cosine theta, d theta. We can do a u substitution for sine theta. That gives us 6 sine squared theta, evaluated from 0 to pi over 2. That gives us 6, I think. I don't know. I feel like I did something sketchy here, but...
So what do you mean? You've never made a mistake. That doesn't count.
Yeah. Okay, so we're going to move on to the one that everyone's been waiting for, which is linear algebra, which I hate to say is not going to be that long or that great because it's like a pretty self-contained class. It is. It's because, you know, maybe it's like an American thing. Like in America, the kind of the pinnacle of high school math education is like, I'm like taking calculus or whatever. And so that provides lots of like prerequisite type knowledge for calculus type classes when you move into college, but hardly any for the other types of classes. I mean, yeah, calculus is great, but it'd be cool to teach high school kids other things. Like compassion. Okay, so here's what I'm going to say for linear algebra, is that what you should be good at the very beginning of the class. Maybe, you know, while I'm sort of riffing here, you guys can put in the comments if you guys have better ideas for this, but I think important getting just right off the ground is solving systems of equations. And you might say, well, that's all of linear algebra. Well, I really hope it's not all of your linear algebra class, because you know there's much more to it, like abstract vector spaces and linear transformations and writing linear operators and matrix representations and stuff like that, and solving systems of equations. Like a lot of problems get down to solving systems of equations at the end, but you know there's a lot more to it than that. Does anyone have any like suggestions?
For Calc 3?
No, for linear algebra, like I said, you know, I was like...
Yeah, I gotcha. Oh. Someone said matrices, but that's just linear algebra.
Yeah, so I would say like, let's do some examples of systems of equations. So we've got 2x minus 3y equals 11. X plus 2y equals 11. This should be a 1. Okay. So, I mean, how would you generally solve this? I think in high school algebra you learn how to solve things with augmented matrices and row reduction. Is that true, Justin?
I didn't, but I think that it's pretty standard for that to be taught like that.
Okay, so you could do that, but generally that is introduced in a linear algebra class. What I would say to be comfortable with is solving systems of equations without just relying on the substitution method. The substitution method is the way that like a lot of students prior to linear algebra seek out to solve a system of equations. So without the substitution method, I would use the elimination method, where I'm taking linear combinations. I guess like before linear algebra, you don't know that word. I would take combinations with scalar multiples of the equations to cancel out variables. So let's notice that if I take these two equations, I multiply the second equation by -2, and I add them, I'll cancel out the x. It'll be super dope. So that'll give me minus 3y minus 4y is minus 7y. Notice my 2x minus 2x canceled. And then I have 1 minus 22, which is minus 21, which gives me y equals 3. Good. So that's cool. And then what should I do from there? We'll probably like plug it into this first equation. That gives me 2x minus 9 equals 1, which is the same thing as saying 2x is 10, which is the same thing as saying x equals 5. So there's my solution. I've got 5 and 3. So let's maybe do one with 3 equations and 3 unknowns. Maybe we'll do it with a matrix, just like based off the fact that, you know, probably you've seen matrix manipulation, like row reduction of a matrix to solve a system of equations beforehand. So let's say we have x plus 2y minus 4z equals 6, and then 2x minus y plus z equals 1, and then minus 3x plus y plus 2z equals minus 8. Okay, so maybe something you would learn in like algebra 2 class in high school or something would be to put this into what's called an augmented matrix. So that's going to be a 3x3 matrix of the coefficients of the left-hand side of this equation, and then like a constant column on the right. So here we have 1, 2, negative 4, 6. So that's just a quick way of writing this first equation. 2, negative 1, 1, 1. That's a quick way of writing that second equation. Negative 3, 1, 2, negative 8. That's a quick way of writing this third equation. And then from here, what you would do is try to do row operations, which is equivalent to our equation operations over here that we did for elimination of variables. Just like pared down to just looking at the numbers in order to get this into so-called reduced row echelon form, which is something that is like defined in a linear algebra class, but it's like a shape of this coefficient matrix, which is seen as the goal when you would see this before a linear algebra class. So you might have learned before linear algebra class that it might be useful to do row operations to zero out these entries in order to work towards our solution. So let's see what row operations would take us there. So I can use row 1 as my tool. So I want to change row 2 and row 3. I could do row 2 minus 2 times row 1 becomes my new row 2. I like to be systematic about this and use the row that I'm using as a tool and put it in the middle, and then on the outside I put the row that I'm changing. But we could simultaneously change row 3, so I could do row 3 plus 3 times row 1 becomes my new row 3. And I did the same sort of system. R1, row 1 was being used as my tool, and I'm changing row 3. So let's see. I'm not changing row 1 in any of these calculations, so I'll just copy it back down. 1, 2, negative 4, 6. Now I'm changing the other two, so I have to be careful with my arithmetic. Row 2 minus 2, row 1. So that's going to be 2 minus 2 times 1, that's 0. Negative 1 minus 2 times 2, that is negative 5. 1 minus 2 times negative 4, that is going to be 9. 1 minus 2 times 6 is going to be negative 11. Is that right? Mm-hmm. Okay, and then same thing here. Negative 3 plus 3 is 0. 1 plus 6 is 7, right? 2 plus 12 is 10. Then negative 8 plus, what's 3 times 6? 18, so that's 10. So we have something like that. And now looking at this, you might say, I need to turn this middle one into a 1. Well, maybe I would do that just by dividing by 5, but that I think is like too much work. Maybe we could do it a little bit more easily, and I think we can if we add these two, so row 2 and row 3, and replace row 2. That'll just put a 2 there, which is a little bit easier to work with. You could get super fancy here and use the Euclidean algorithm to write 1 as a linear combination of 5 and 7, but we won't get there. Okay, so maybe we'll do row 3 plus row 2 becomes my new row 3. Okay, so sorry, becomes my new, well, sorry, I did this wrong. row 2 plus row 3 becomes my new row 2. Okay, so 1, 2, negative 4, 6, 0, 2, because negative 5 plus 7 is 2, and then 19, and then negative 1. So I've got something like that. And then 0, 7, 10, and 10.
Somebody's saying in your middle step there, your first 10 should be negative.
This 10?
Yeah, the one in the 3x3.
Yeah, so it should also not be 10. No, it should be 10. Okay, so we've got something like that. And then where should we go from here? Maybe let's take this 2 and use it to zero this 2 out. So that means we'll do row 1 minus row 2 becomes our new row 1. So let's see. That'll give us 1, 0. Let's see. This minus this will be like negative 23. And then 6 minus negative 1 will be 7. And then we have 0, 2, 19, negative 1, 0, 7, negative 10, 10. All right, so we're left with something like that. Now let's put that over here and see where we can take that. So we've got 1, 0, negative 23, 7, and then 0. I'm gonna like divide row 2 by, actually I'm gonna swap row 2 and row 3 right now. So 0, 7, negative 10, 10. So that's swapping row 2 and row 3, and then 0, 2, 19, negative 1. Great. And now I have a clear way of turning this 7 into a 1 by subtracting 3 times 2. So let's do that. So we'll do row 2 minus 3 times row 3 becomes my new row 2. Maybe this will be the last one that I do because this is getting to be cumbersome. So 1, 0, negative 23, 7, so that's my first row. My third row is also not changing, so 0, 2, 19, negative 1. And then I've got 7 minus 6 is 1. Then I've got negative 10 minus 3 times 19. What's that? It's impossible to know. What's 19 times 3? It's like 27. Negative 67. And then 10 plus 3 is 13. So we have something that looks like that. And maybe we'll cut this one off right here. I think maybe your next step would be to turn this 2 into a 0 by subtracting 2 times 1, and then you can go from there. So let's see. In the end, you'll get x equals 2, y equals 0, and z equals negative 1, assuming that I haven't made any arithmetic mistakes along the way.
Negative 68.
Negative 68.
I trust the first possible comment.
Assuming that I haven't made any mistakes along the way, which is a big assumption. Okay, great. So I hate to say it, is there anything in the chat about like suggestions for linear algebra other than...
Let me see. I saw Gaussian elimination. Some people said just basic geometry is good.
So this is Gaussian elimination.
Yeah, that was just before you did.
What we just did.
Yeah.
Yeah, but just in case people don't know the terms.
Yeah. Linear transformation, pretty much what we've been doing.
Yeah.
I'll scroll up quickly, but think anything crazy.
Yeah, it's kind of a self-contained class. Like, it's not quite as self-contained as an introduction to proofwriting class or something like that, where you truly could just show up having not taken math in a long time and have an open mind and be fine. But you know, it's like close. It's much easier to jump into than calculus, where you're assumed to have like all of these like other skills in the background. I mean, not to say that it's easy though. I mean, yeah, that's.
Yeah, I think matrix inversion's just linear algebra.
No, yeah, that's like no.
It's in the class.
Yeah.
I remembered we did this, but we did it on calculators. They didn't teach us how to do it.
Oh, cool.
Yeah, they just told you to run a calculator and how'd you do it. So I missed out.
Okay, what do you need to know to start differential equations? So here are the things that I would say are important to have on day one. So first would be integration techniques. So we reviewed like a bunch of use substitution to be good on day one of Calculus 2, but you learn lots of integration techniques in the Calculus 2 or an integral calculus type class, and you're going to reuse a lot of them in differential equations. So like trig substitution, partial fraction decomposition, etc. Like integration by parts, stuff like that. All of that is going to be important to be fairly solid at. So number 2 would be series. So generally there's a big section of the class where you do series solutions to differential equations. So you'll need to know like basic series or series of some basic functions and maybe some rules about convergence. Actually, the rules about the convergence are not super important for differential equations. That's sort of neither here nor there. I guess they are. You'll do a series solution technique and then check the convergence at the end. So you delete that. Okay, and then the third thing would be linear algebra. So some schools have linear algebra as a prerequisite. Some of them have it as a co-requisite. You got to know some linear algebra for the back half of differential equations. You're going to especially need good knowledge of eigenvectors and eigenvalues. When you solve systems of linear equations, you'll use matrix methods. Okay, let's look at some examples.
I think for my school, it wasn't even required at ODU for linear algebra wasn't required, co-requisite or prerequisite. You could just take it.
Cool. Okay, so let's maybe do this first. All right, so what integration technique would be used here? We've got a polynomial function times a transcendental function. That screams out to use integration by parts. There's this nice method called the tabular method for integration by parts. Steve Chow, Blackman Red Pen, I hope his name is not secret, calls it like the DI method. So he puts a D here and an I here.
$300.
That's, geez.
I know, right?
Thank you. That's just labeling the column of the derivative in the integral. All right, so how do you do this? Well, you take the function whose derivative will eventually zero out and you put that in the D column. So that'll be the polynomial. Just did an interval of backflips over there. It's like CrossFit or something.
And then 300 BRLs. There's only $50, but still. It doesn't look like it. It has the dollar sign. It's only one. Yeah.
I was tricked.
I had it cut off on my check. I couldn't see the R. It's okay. It was worth the backflip. You just
No, okay, but now, I mean, like, I guess you guys see that I'm in for it.
Yeah.
Okay, and then you take antiderivatives on this side. So the derivative of x squared is 2x, 2, 0. So we know how to take derivatives here, right? We're all friends. E to the x, e to the x, e to the x, those are antiderivatives. Then you match on the diagonal. And you vary sign. So that's a plus, that's a minus, that's a plus. That gives us our strategy. So this gives us our antiderivative of x squared e to the x plus 2x e to the x. Sorry, minus 2x e to the x plus 2 e to the x. We got it. Okay, let's do another one. So let's do the antiderivative of...
I'm telling you to take a break. Somebody said if you add shipping and handling, it's 6 backflips. That's the extra.
Okay, so let's say we have this function we just take the antiderivative of. So this screams out, since it's got like this irreducible quadratic under the radical, this tells us that we should probably use trigonometric substitution, in fact, tangent substitution. So what we'll do is take x and set it equal to 4 times tangent theta. So why is it 4 times tangent theta? It's because 16 is 4 squared. So notice that means that x squared plus 4 is the same thing as 4 secant squared theta. So that's using trig identities. 1 plus tan squared is secant squared. And then dx is equal to 4 secant squared theta d theta. That's just using derivative of tangent is secant squared. So where does that leave us? So we've got 4 secant squared theta d theta up top. So that's from our dx. We've got x squared, which is 16 tangent squared theta. Then we have the square root of... Let's see. 4 secant squared theta. 4 secant squared theta. So we have something like that going on. So let's rip all of this into sines and cosines. Well, let's see what our number is. So we have 16 times 2, that's 32. So we've got 1 over 8. So this is equal to 1 by 8. And then we have 1 over cosine squared theta over sine squared over cosine squared theta times 1 over cosine theta d theta. So we're left with something like that. Tangent is sine over cosine. Secant is 1 over cosine. So this cancels this. This flips up, and we're left with 1 over 8. Then the integral of cos theta d theta over sine squared theta. We're left with something like that. So now we could say u is equal to sine theta. That makes du equal to cos theta d theta, and that leaves us with 1 over 8 du over u squared, which is going to be negative 1 over 8 u. Taking the antiderivative using the power rule. So that's going to give us negative 1 over 8 times sine theta plus a constant. Now we have to figure out sine theta. So let's do that down here. So we know x equals 4 tangent. That means tangent equals x over 4. So if we make our triangle, put our angle theta here, our right angle here, x is the opposite over the adjacent, so x4, this gives us the square root of x squared plus 4 plus 16 right there. Sine is equal to adjacent over hypotenuse, but I have that in the denominator, so that's going to leave me with minus square root of x squared plus 16 over x plus a constant. Then I need an 8 there. So I'm left with something like that. So kind of gnarly, but not too bad. Okay, let's do Another one.
When did you do your first backflip? Like what age?
Oh, like 7.
You got a little bit of experience then, too.
Yeah. All right.
Pretty cool.
Let's see. Let's do this one. So the integral of 3x plus 4 over x squared plus 4 times 3 minus x. So this is the antiderivative of a rational function. So antiderivative of a rational function motivates us to use partial fraction decomposition. First thing to check is the degree of the numerator versus the degree of the denominator. The degree of the numerator is less than the degree of the denominator, so there's no step to do first. If the degree of the numerator was bigger, you would have to do polynomial long division. Okay, so now what we do is set up our decomposition. So we have 3x plus 4 over x squared plus 4 times 3 minus x. That's our integrand. And we're going to write this as a over 3 minus x. So that's our linear term. And then plus something over x squared plus 4. But since that's an irreducible quadratic, we need a bx plus c there. Just kind of for reasons about kind of how these things work out. So now we can turn this from an equation about rational functions to an equation about polynomials by multiplying by something which will cancel out the denominator. So that'll be 3 minus x times x squared plus 4. Okay, so on the left-hand side, we're left with 3x plus 4. On the right-hand side, we'll be left with a times x squared plus 4 plus bx plus c times 3 minus x. So we're left with something like that. And now we can do a bit of a trick to get a very, very quickly. So let's do that trick by setting, so let's set x equal to 3. Let's notice that gives us 3 times 3, which is 9, plus 4, which is 13 over here on the left-hand side. And on the right-hand side, we have a times, so 3 squared is 9, plus 4 is 13. That, and then plus the rest of this, but the rest of the stuff zeroes out because we have 3 minus 3. So this tells us immediately that a equals 1. Okay, so that's pretty nice. So that means that we have really 3x plus 4 equals x squared plus 4 plus bx plus c times 3 minus x. We can replace a with 1 immediately. Okay, then we can move some things around. Now we can kind of use that trick for b and c, but you'd have to jump into complex numbers. You'd have to set x equal to, plus and minus 2i, and it's maybe not super worth it. So what I would do instead is rewrite this as bx plus c times 3 minus x equals 3x minus x squared. That's what we get from moving this stuff over. But now immediately you can kind of see what's going on. Notice this 3x minus x squared is essentially equal to x times 3 minus x. Now this is really lucky in this case. Often you would need to set up a system of equations. But, I think it's really nice to look for, trick strategies that jump out in just particular examples like this one right here. Now we can cancel this and this, and we get bx plus c equals x. But let's recall this has to be true for all x. So since this has to be true for all x, the coefficients of x and the constants on each side have to be equal. That tells us that b is equal to 1 and c is equal to 0. That tells us that this integral decomposes into 1 over 3 minus x plus, what did I say? B was equal to 1, so x over x squared plus 4 dx. So we're left with that integral right there. It's cool how that worked out. So let's see what we get. So notice that we could multiply this by a half if we multiply the numerator by 2, and then we see the derivative of the denominator is inside the numerator right here. That tells us we could do a u substitution, although to be honest, now we're preparing for a differential equations class, so these types of quick u substitutions should probably be done in the background. So this is going to give us minus natural log of the absolute value of 3 minus x for this one, and then plus 1/2 times the natural log of the absolute value of x squared plus 4 plus a constant. So you got something like that. And then, I don't know, if you're like feeling excited, you could put these natural logs together and get the square root of x squared plus 4 over 3 minus x plus a constant. Oh, and then you could take this absolute value and then change the 3 minus x to an x minus 3, so you don't like look like a psychopath with 3 minus x instead of x minus 3 when you've got a choice. And then I think this would be a nice sort of way to write the solution to this problem. Okay, so now let's look at some power series. So let's find power series. So in calculus 2 or something, you do power series via Taylor expansion or Maclaurin expansion, or just manipulation of known power series. It turns out that this manipulation of known power series is like quite a bit more useful and easier to work with, and it shows up in the differential equations setting a lot more, and it's like a good combinatorial tool if you've ever like seen the videos I've done with generating functions and stuff. So anyway, let's find the power series for this guy. Let's say we've got f of x equals the inverse tangent of 2x. Okay, so how would you do this? Well, maybe you would do something like this. Let's note that I know that 1 over 1 minus u is a geometric series, which can be written as the sum as n goes from...
I'm verifying. This is $50. I think it's €50, but it's enough to put us to the next 50.
Okay, I got to do a backflip. Okay, so good. So we've got something like that. But notice if I set u equal to, what do I need it to be equal to? Maybe 2x squared. Actually, maybe it'll be negative 2x squared. That's going to give me 1 over 1 plus 2x quantity squared equals the sum as n goes from 0 up to infinity of 2 to the n, x to the n. That should be a n there.
Say hi to Penn, Red Pen. He's in chat.
Oh, hey. Okay, so we have something like that, and this doesn't seem maybe super helpful, but if you look at this guy right here, this is pretty close to the derivative of the arctan of 2x. So that gives us like a motivating path to finding that power series from this known power series, which is a geometric series. So let's do f prime of x. So that's going to be 2 over 1 plus 2x quantity squared. But that's like essentially what we have over here. We just need to multiply it by 2. So let's take this, multiply it by 2. That puts a n plus 1 there. So that means the derivative is equal to the sum as n goes from 0 to infinity of 2 to the n plus 1 x to the n. But if the derivative is equal to that, then the function is equal to the antiderivative of that, the term by term antiderivative. So that's going to give us the sum as n goes from 0 to infinity of 2 to the n plus 1 x to the n plus 1 over n plus 1. You might say, well, what about the constant that comes from taking the antiderivative? But notice the constant that would come from taking the antiderivative cancels out from the fact that we know our function is the inverse tangent, which is equal to 0 when x is equal to 0, which means that c is equal to 0. So we're left with something like that. I don't know, you would maybe want to reindex that, but I would say that's kind of neither here nor there. I don't think you really need to do that. Okay, let's do another one maybe? Okay, so let's do maybe g of x equals x squared over 2 minus x, actually let's say just x over 2 minus x squared. So we have something like that. Now we're going to play the same game. We're going to manipulate known power series, in fact really just geometric series to get us to the right picture. So again, we know 1 over 1 minus u is the sum as n goes from 0 up to infinity of u to the n. But we've got something squared in the denominator. Actually, let's take care of this 2 first. So how could we do something with this 2? Let's maybe replace u with x over 2. So that gives us 1 over 1 minus x over 2 equals the sum as n goes from 0 to infinity of x to the n over 2 to the n. Then we can multiply the numerator and the denominator of this by 2, giving us 2 over 2 minus x. Okay, so I think that's a good place to be at the moment. Now, what happens if we take the derivative of this? So d by dx. So this is close to like the best friend derivative. Am I right in there? Black pen, red pen? This is like the, so the derivative of this function is almost its square. If we take the derivative of this, we get 2 over 2 minus x squared. You can check that with the power rule and the chain rule or whatever. Okay, so that means that motivates us to take the derivative of this guy too. So we'll need to take the derivative of this too, but we'll pick that up over here. Okay, so things have gotten out of hand over here, but let's just pick up from this. Let's copy this over. We have 2 over 2 minus x quantity squared equals the derivative of this power series. So that's going to be the sum as n goes from 0 up to infinity of n times x to the n minus 1 over 2 to the n. But now we're home free. Notice our g of x is exactly that, but with an x in the numerator instead of a 2 in the numerator. So I can get rid of the 2 in the numerator by multiplying by a half. I can put an x in the numerator by multiplying by x, and that kills this like minus 1 here, and I've got it. And this is like, you know, to be fair, I think a less systematic way that I would approach one of these problems than like inside the Calculus 2 class. But that being said, I think this is a more like exploratory way of approaching one of these, and this exploratory way is a good way to approach it after you're done with the class and you're just kind of remembering something from a previous class, because it really helps to like build the intuition. Okay, so anyway, let's move on to linear algebra stuff that shows up in differential equations. And in general, that's like finding eigenvectors and eigenvalues. Justin, could you bang this on the wall outside? Look how chalky this is, guys. Okay. So let's find eigenvectors, eigenvalues, diagonalize. Because like the trick is like if you found eigenvectors and eigenvalues, then you've found the diagonalization procedure for a matrix. So let's say we start with this matrix, so 2 by 2. We'll do 2 examples. We'll do a 2 by 2 and we'll do a 3 by 3. That's like kind of enough, and really just kind of need to remember the procedure. In fact, when I'm teaching like differential equations, what I'll generally do is like have everyone remember the procedure and do a couple by hand, and then we can like use a computer or whatever to do it after we remember the procedure. Okay, so first thing that you need to do is find the eigenvalues. So I'll just put right here the eigenvalues. So let's recall that those are roots of the characteristic polynomial. So that means we need to find the characteristic polynomial. That's the determinant of x times the identity matrix minus our matrix. Sometimes that's done in the other order, but it doesn't really matter. So let's see, that's going to be the determinant of what matrix? So we've got, let's be really thorough, x, 0, 0, x minus our matrix, which is 0, 1, minus 2, minus 3. So we've got something like that. That means we need to find the determinant of x minus 0 is x, 0 minus 1 is negative 1, 0 minus negative 2 is 2, x minus negative 3 is x plus 3. So our eigenvalues are roots of this characteristic polynomial. This characteristic polynomial is the determinant of this matrix, which ends up being x squared plus 3x minus 2. From determinant rule, remember it's AD minus BC. Okay, so let's bring that up here. We have our characteristic polynomial. X squared minus 3x, sorry, that's plus 3x minus 2. Did I make a mistake here? I did make a mistake. What's my mistake? There should be a plus 2 here. AD minus BC, the minus signs cancel. Okay, so now we need to look for 2 numbers that multiply to give us 2 and add to give us 3. But, you know, we're reviewing for differential equations, so we probably don't need to labor that. So what does that tell us? Our roots are negative 1 and negative 2, which means we have 2 eigenvalues. So we've got eigenvalues, lambda 1 maybe, which is negative 1, lambda 2, which is negative 2. So there are our eigenvalues. Now we have to find the eigenspace for each of those eigenvalues, but since we've got 2 eigenvalues and we've got a 2 by 2 matrix, we know the eigenspace is going to be one-dimensional, so just going to be with one eigenvector each. Okay, so let's find the eigenvectors. So let's say vectors, and let's do lambda 1 equals negative 1 first. So in order to find the eigenvectors, so I'm not going through the theory here, but in order to find the eigenvectors, you want to look at a certain null space. So you want to look at the null space of negative the identity. Well, really it's lambda 1 times the identity minus our matrix. But in this case, it's just the null space of minus identity minus our matrix because of the setup that we have. Okay, so that's going to be the null space of, let's see, what is that? We can actually go down here and just plug in x equals minus 1 into this matrix and get a real quick picture of it. So we get minus 1, minus 1, minus 1, minus 1. And then down here we get 2, 2. So 2, 2. But now let's recall that the null space of a matrix is not changed under row operations. So that means we can compute row operations and we keep the same null space. So this is clearly row equivalent to the matrix 1, 1, 0, 0. I don't know, just multiply this by 2 and add it to that one, that cancels, and then scale the first one by minus 1. And then you've got that. So it's the null space of this. So now let's take a vector. Let's maybe call our vector xy, and let's say our vector is inside this null space. but being inside that null space means you're annihilated by the matrix. So 1, 1, 0, 0 times xy is equal to the 0 vector. That's being in the null space. But that gives us an equation, x plus y equals 0. That's the equation it gives us. That tells us that y equals negative x. But then x is a free variable, or y is a free variable, depending on how you want to do it. But that gives us a vector of 1, negative 1, just by choosing x to be 1, right? So that's our eigenvector. So the eigenvector associated to negative 1 is, we'll call it v1, which is 1, negative 1. Something like that. And now let's notice, now that we're talking about differential equations and we're not like in calculus review of vectors, I didn't put a line, an arrow over it, because now we're in fancier math classes. We don't need arrows over our vectors. We're like big kids now. Okay, so anyway, that's our eigenvector for this eigenvalue, and now you would play the same game for our other eigenvector. So let's do that. Okay, so let's do lambda 2 equals negative 2. So that means I need to look at the null space of, let's just jump right to the matrix. So it's going to be this matrix with negative 2 plugged in for x based off of what we saw. So that's going to give us negative 2, negative 1, 2, 2, 1. Great. But that row reduces pretty easily to 2, 1, 0, 0. Now that's not reduced row echelon form, but for our purposes that's like good enough. Okay, so now let's take something in the null space here. So let's call it xy again, just for freedom. And then being in the null space means you're annihilated by that matrix. But, you know, like I said, the null space is invariant under a row operation, so being annihilated by this matrix is the same thing as being annihilated by this matrix. So we've got this times xy equals the 0 vector, so that means that 2x plus y equals the 0 vector. Sorry, equals the 0, so that means that y equals minus 2x. So that means we could take x to be equal to 1, and that gives us our eigenvector v2, which is 1, negative 2. So there we've got our eigenvector for v2. Okay, so let's put that in here. So v2 is equal to 1, negative 2. So there we've got our eigensystem. That's the like Mathematica way to find it all at once. Eigensystem of a matrix. So we've got that, and then we have this. So now let's see what that does for diagonalization. Okay, so that tells us that if we set P equal to a matrix built out of the eigenvectors, so I'll put V1 in the first column, V2 in the second column, so 1, negative 1, 1, negative 2, then P inverse AP is equal to the diagonalized matrix. So that would be like negative 1, 0, 0, negative 2. And it's in that order because here we have the eigenvector for negative 1. Negative 1 goes here. Eigenvector for negative 2. Negative 2 goes here. Those eigenvalues are on the correct part of the diagonal. Okay. And then the picture that's going on here, if you're interested, is this. You've got like, let's say we've got R2, and then I'll put a standard ST for standard basis. R2 ST for a standard basis, and then we've got this map from R2 to R2, which is our matrix A, and then down here we've got R2 with our basis of eigenvectors. I'll put B here, so R2 with our basis of eigenvectors. So just like I said, our basis of eigenvectors, so that'll be made up of 1, negative 1, 1, negative 2. There's our basis of eigenvectors. And down here, our map is this diagonal matrix, -1, 0, 0, -2. Great, and then what is P? Well, P transports us from R2 in the standard basis to R2 in the basis of eigenvectors. And you know, I have to be careful about which way it goes. So let's see, we go from here to here. Okay, so it goes like this. P, and then P inverse. There, it goes something like this. So notice if we were to go PA, P inverse, you get the same thing as this diagonal. Keeping in mind that these are mappings, so you work from the right, PA, P inverse. So this is the picture right here. I mean, this is like this is called a commutative diagram. This is like super important and beautiful way to think about these things is like via these diagrams. So like this matrix A is really just like you've got an abstract linear transformation. You've got an abstract linear transformation which is just happening on the abstract vector space, or maybe like the abstract two-dimensional vector space V. And then, depending on what basis you take for this abstract two-dimensional vector space V, I should say, this abstract linear transformation takes different matrix forms. And in this matrix form down here, it's like super nice. That's the whole idea behind all of this. And this is like the big idea about linear algebra. You've got vector spaces, you've got linear transformations between vector spaces. Picking a basis allows you to represent these linear transformations as matrices. Linear algebra is not really a study of matrices, it's a study of like vector spaces and linear transformations. It just happens that if you're in finite dimensional vector spaces, everything can be represented by a matrix and everything can be represented by a column vector like these things over here, but that's really kind of missing the point or whatever. I mean, but you know, that being said, if that's what it kind of takes for you guys to get through the class, then that's also fine. Okay. So let's set up a 3x3, but not do the whole thing because it's like super gnarly. It's not that fun. Okay. So let's do the same kind of thing. Let's say we've got this matrix B, which is 2, 2, -2, 1, 3, -1, -1, 1, 1. So let's say that's our B. So, you know, we have the potential of having 3 eigenvalues and 3 eigenvectors. You know, we may not have 3 eigenvalues and we may not have 3 eigenvectors. That's a whole thing about diagonalizability and stuff like that, which, you know, we won't cover here. All of that stuff is kind of like well reviewed in a differential equations class. What happens if you have a non-diagonalizable matrix when you're looking at a system of differential equations? Okay, so anyway, PBX. So that's going to be what? The determinant of, I think we can do this all at once. It'll be x minus 2, -2, 2, -1, x minus 3, 1, 1, -1, x plus 1. We got something like that. Now we can do like so-called cofactor expansion. So that means we like cross out the first row in the first column and take the determinant of the sub 2 by 2 and multiply it by whatever's in the crosshairs. So this is going to be x minus 2 times the determinant of this sub 2 by 2. That'll be x minus 3, x plus 1 plus 1. Okay. Then we'll have plus 2 times what's going on here. Now I pulled a fast one over on you. Really a minus sign is built into this, but there's a minus sign built into the 2.
X minus 1 is the last entry.
Great. But some minus signs canceled. And then we have the determinant of -1, 1, 1, x minus 1. So that's going to be like 1 minus x minus 1. Is that right? Something like that. And then we have plus 2 times the determinant of the submatrix right here. So that's going to be 1 minus this. So that's going to be 1 plus 3, so that's going to be 4 minus x. So we're going to be left with something like this. Then we can start simplifying this a little bit. Let's see, what is this going to multiply out to? X squared minus 4x minus 2. And then this is just going to be minus x. And so we've got something like x minus 2 times x squared minus 4x minus 2 minus 2x minus another 2x plus 8 from that down there. And then, I don't know. Actually, we can do this because it's not actually that bad. Okay, so let's see where we can take this. We can at least get the eigenvalues. We won't worry about the eigenvectors. Okay, so we've got PB of x equals, I feel like I made a mistake. I did. This should be 4. This should be plus 4. Okay, so I've got x minus 2, and then x squared minus 4x plus 4, and then let's notice that this is minus 4x plus 8. I can factor a minus 4 out of that, and I have an x minus 2. That allows me to write this as x minus 2, and then x squared minus 4x. Notice that the minus 4 cancels with this 4. We're factoring out this whole x minus 2. Which means we just need to take the difference of these two things. Okay, so this gives us x minus 2, x minus 4 times x. So that means our values, our eigenvalues, are lambda 1 is 0, lambda 2 is 2, lambda 4 is 4. So something like that. Okay, and then you find the eigenvectors the same sort of way. So that would be like, exactly the same as we did before. Maybe we'll find the eigenvector associated with the eigenvalue of 0 just to do a little bit of it. And that's maybe the quickest one to do. So notice finding an eigenvector. So if the eigenvector for this, so eigenvector V1 is in fact in the null space of B, because it's in the null space of B minus 0 times the identity matrix. But that's just B minus 0. So that means we really just need to look at the null space of this guy right here. But again, we can do that with row operations. So this is the null space of, let's maybe bring this 1, 3, negative 1 to the top, 1, 3, negative 1 to the top. And then we can, maybe in the second row, we'll do this row, or this first row minus 2 times this row. So this will be 2 minus 2 is 0. 2 minus 6 is negative 4. Negative 2 minus negative 2 is 0. So we've got something like that. And then we'll add these two and put it here. So that'll be 0, 4, 0. So we've got something like that. But notice that's going to be the same thing as the null space of 1, 3, minus 1, 0, 1, 0, 0, 0, 0. By simple row operation to get us there. Again, this would be like, this is like review after having taken linear algebra. And then let's see, this 1 can be used to cancel this 3. If this were not 0, it would have some sort of effect on the rest of it, but it is 0. Now let's take something in the null space here, x, y, z. Oh, I noticed like students being a little bit like weirded out by this at the beginning, but this element sign, it's multi-directional. So you can put it in any direction you want. If you've got an element here that needs to be in something here, you can just like face it in that direction and you've got it. If you want to know how to put it in tech, it's /ni. It's in backwards. Math people are real funny. Okay, so let's see. That means that this matrix 1, 0, minus 1, 0, 1, 0, 0, 0, 0, x, y, z equals 0, 0, 0. That's what it means to be in the null space. That means that x minus z equals 0, and that means y equals 0. And then, I don't know, like if you want to get fancy about it, since this is not a pivot column, that means that z is your free variable. So you can set z equal to 1, and you'll get x equal 1, z equal 1, and then y is equal to 0. Again, because it's your free variable, that gives us your eigenvector for this. So v1 is equal to 1, 0, 1. Great. And then to find the other ones, you do the same kind of thing, except you don't find the null space of the parent matrix. You find the null space of like the kind of associated matrix. Okay, now we're into, I was about to say now we're into fun classes, but that makes it sound like the other classes aren't fun. All math is good. I thought about making this video where we do like a tier list of math subjects. But then everything just gets S tier because math is just so awesome. That's the thing. Like this was like how the video was gonna go. We're workshopping a video right now, if you guys hadn't noticed. So I was gonna be like, okay, we're gonna make a tier list of math classes or whatever, and then like we just deliberated hardcore on all the classes, but then they all ended up being S tier. Is that a good idea or not a good idea?
Then the punchline is your favorite, and there's a double S tier above it. That's revealed.
Oh, that's a good point. Justin just came up with a great idea. And then the last one that we look at will be my actual favorite. And we scroll it down, and there's actually a double S tier. This is great. Maybe this will be on Wacky Wednesday. You know, second channel, mathmajor.com, we have like, oh yeah, I bought a domain, but I haven't done anything with it yet. The second channel, Math Major, has Wacky Wednesday where we do weird videos. Maybe we'll do a studio tour. Do you guys want to see a studio tour? Oh, here's another video that I thought about pitching. This would go on, I don't know where this would go. So I've been vegan for like 25 years, and there are all these popular videos on YouTube like, I went vegan for 30 days. You won't believe what happened. I want to make a joke video where I went vegan for 25 years, and you won't believe what happened. Okay, anyway.
Then make it like just a story about your life and just completely ignore the vegan part for the entire time.
Yeah, that would be good. Yeah. Okay, abstract algebra. Now we're getting into the fun stuff. You know, like in the US, schools are messed up. There's this fancy prep school in town that teaches abstract algebra to its like smart high school students. But like the kids at the public school don't get that opportunity. This is outrageous. Okay, so what are some important things to know? Are there any comments about my banging video ideas?
People said they want a studio tour. People are excited for abstract algebra. Somebody said you should make some of those for April Fools.
Okay. Important to know congruence mod in. Where would you learn a congruence mod in? Probably a intro to proofs class. So you'd learn about congruence mod in an intro to proofs class. You might say, well, why aren't we talking about what you need to know coming into an intro to proofs class? Because that is truly one where you don't need anything to enter that class. That should be taught kind of from the bottom. But you should remember congruence mod in once you've started abstract algebra. Also proofs by induction. Also basics of functions. So, you know, injective functions, surjective functions, when a function is invertible and stuff like that. And then basics of proofs. I mean, that kind of goes without saying, given the fact that I just said induction right here. Okay, so let's do some examples. So first example will be congruence mod n. And let's highlight that with an addition. Addition / multiplication table mod 8. So in other words, an addition and multiplication table of Z8. So generally, when you're learning about congruence mod n in an intro to proofs class, you would learn about equivalence classes as well, and you would learn about Z8. You won't learn that it's a group or it's a ring, but you will learn that it exists. You won't just give a name to it. So I know when I teach an intro to proofs class, we generally make these tables. They're not that hard. Okay, so let's recall that Z8 is equal to 0, 1, 2, 3, 4, 5, 6, 7. I put bars over all of them because by bar, I really mean the equivalence class. So, for example, 3 bar is going to be all integers n such that n is congruent to 3 modulo 8. This is this is like standard notation for the z's, but it's maybe not standard notation for an arbitrary equivalence class. You'd maybe put brackets. So maybe let's put brackets over here. You would also maybe see that as bracket 3. So what do we get here? So you'll get 3, 11. Notice 3 plus 8 is 11. That means that 11 minus 3 is a multiple of 8. 19, 27. Then back this way, negative 5, negative 13, and so on and so forth. So this is your equivalence class. Okay, so now let's make an addition table. Maybe we'll see if we make the whole thing. So 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5. I only had room for 6 in this direction. Okay, so what am I doing? Well, I'm adding these things, but after every step, I'll reduce mod 8. That's what it means to be within the space of equivalence classes inside of Z8. So let's just pick a couple of these entries right here. So 3 plus, let's go down here, 3 plus 6 is 9, but 9 is congruent to 1 mod 8. So you would in fact put 1 here instead of 9 because you would do the reduction. You want this addition to be closed. Then let's maybe do 4 plus 7, that's 11. Well, that's 2 because that is 2 more than a multiple of 8. Then 5 plus 6, that's also 11, so that would also give us 2. And then, well, a lot of these others are just kind of exactly what you would think they would be. So 2 plus 4, that'll be equal to 6, because you don't need to divide by 8 and keep the remainder there. It's between 0 and 7. 2 plus 6 is 0. 2 plus 7 is 1. 2 plus 5 is 7. 2 plus 3 is 5. You can see this is 4, 3, 2, right? Okay, so again, there's like not much to this. You just add the two numbers, divide by 8, and keep the remainder. Okay, so let's maybe not make a full multiplication table. Let's just do some examples of multiplication in Z8.
Oh, 6 plus 5 should be 3. Because 11 is 3 more than 8.
Oh, yeah. Great, cool. So let's do some examples of multiplication. So let's do 3 times 7. So 3 times 7 is 21, but if we reduce that mod 8, we'll notice that we get that is 5? Yeah, that's 5 because it's 5 more than 16. So this is, 5. Good. And then maybe like 4 times 4. So 4 times 4. So 4 times 4 is 16, but that's 0. Well, notice we just multiplied two things that were non-zero and got something that was 0. So something weird is going on here that doesn't happen, like, for instance, in the real numbers. Notice that 5 times 7, so 5 times 7 is 35, but 35 is 3 more than a multiple of 8, so this is 3, because it's 3 more than 32. So multiply the two numbers, divide by 8, and keep the remainder. Okay, so that would be like, that's really all I'll say about congruence mod, and there are some more things to do, but I think, you know, we'll look at other examples as well. So let's look at some induction examples. Okay, so let's prove that for all natural numbers n, 1 cubed plus 2 cubed plus 3 cubed plus ending at n cubed is equal to n squared times n plus 1 squared over 4. Okay, so we would do this with induction because we're trying to prove a statement for all natural numbers. Induction is kind of the standard thing that would jump out first. So in an inductive proof, you want to start with the base case. So that would be the case for the first natural number, which is n equals 1. And notice that everything is okay here because we have 1 cubed is, in fact, the same thing as 1 squared times 1 plus 1 squared over 4. So we're good to go there. The base case checks out. And now we make an induction hypothesis. So an induction hypothesis, so in this case it would be, well, we'll suppose for some k bigger than or equal to 1, we have this statement holds, so 1 cubed plus 2 cubed all the way up to k cubed equals k squared times k plus 1 squared over 4. So we make an induction hypothesis, and after making the induction hypothesis, we look at the next case. So what is that next case going to be? So that'll be the k plus first case. So how would we write that out? I would say we would do this. Now consider, like I said, the next case. That'll be 1 cubed plus 2 cubed, ending at k plus 1 cubed, but I'll put a k cubed in there. So we've got k cubed plus k plus 1 cubed. Great. But what tools do we have? We have the induction hypothesis and perhaps the base case, and then just plain old arithmetic, really symbolic manipulation. So we could take these first k terms and apply the induction hypothesis. So that'll leave us with k squared times k plus 1 squared over 4 plus k plus 1 cubed. Something like that. So again, what I did is I took the induction hypothesis and applied it to these first k cases. Okay, sick. So what should we do now? Well, I think a mistake would be to multiply everything out and then try to factor it. That would be super gnar. What I would do instead is notice that I've got k plus 1 squared here, k plus 1 cubed here. I can factor out a k plus 1 squared. So let's do that. But before we do that, let's also set ourselves up for success a different way, and that's multiply this by 4 over 4 just to make my denominator the same. Okay, now I can take a k plus 1 squared out of this. Let's go ahead and take a 4 out of the denominator as well. And then what am I left with? Well, after that factorization, I'm left with a k squared here. And then here I'm left with a 4 times the quantity k plus 1. Right, because I took everything else out. But this 4 times k plus 1 is the same thing as 4k plus 4, but 4k plus 4 factors to k plus 2 quantity squared. Then mashing this all together, I have k plus 1 squared times, and then if you want to be real like pedantic about it, k plus 1 squared over 4. But that finishes this induction step, which is exactly what we needed in order to finish this proof. Okay, sweet. So let's now look at like some basic techniques of proof, maybe like using divisibility and stuff. Okay, so maybe let's call this proposition so we sound fancy. So let's prove that if 4 divides a squared plus b squared, then a and b are both not odd. This is not at all the most efficient way to write this down, but I think it's presented like this in order to have you carefully decode what the logical statement is here. Well, if they're both not odd, then they both have to be even. So we could replace that with a and b are both even. Now, how do we want to prove this? Well, I think maybe our best bet would be to prove it by contrapositive. I think maybe this is a nice setup for contrapositive proof because the conclusion has a simpler statement than the hypothesis. And you generally want to prove from simple statement to more complicated statement. And that means we have to do a reversal here, but that reversal can be done, like I said, with the contrapositive. So I don't know, maybe you would say, I'm going to do this by contrapositive. Positive. So let's suppose that A and B are not both not odd. Oh, that's super gross, right? That's super gross. But remember, the contrapositive of the statement P implies Q is the statement not Q implies not P. So we're like knotting that conclusion. Okay, well, maybe in other words, what is it? One of them is odd. Yeah. In other words, one of A or B is odd. And I guess I should say not one, but at least. So at least. That would be the negation of this like super gnarly statement right here. Okay, so without loss of generality, assume A is odd. How do I know we can do this without loss of generality? That's because in this whole setup right here, A and B are playing symmetric roles. Okay. Okay, so now write A equals 2C plus 1 and observe that A squared plus B squared equals 2C plus 1 squared plus B squared, which equals 4C squared plus 4C plus B squared plus 1. So we've got something like that, okay? But notice that that is congruent to B squared plus 1 mod 4, right? Because we got all those multiples of 4 in there. And then, I don't know, like, you could maybe do this with two cases at the end. So case number 1, B is even. And then case number 2, B is odd. So if B is even, then B squared is a multiple of 4. If B is odd, then B is 1 mod 4. So in this case, you get this is congruent to 1 mod 4. In this case, you get this is congruent to 2 mod 4. If you want to work these cases out like super carefully, you could just say here B is 2D and here B is 2D plus 1. And you square them. Notice here you get a multiple of 4, so that'll cancel with this thing. And then 45 cents.
45 cents to the next flip, yeah.
And then this is like going to square to something that has a remainder of 1. Pretty similar to the squaring up here. Anyway, what we get here, either way we look at it, we have a squared plus b squared is not congruent to 0 mod 4, which tells us that 4 does not divide a squared plus b squared, which is where we wanted to end up with the contrapositive like style of proof. Okay, cool. So let's do another one. Okay, so let's solve over the integers. In other words, like the video I make when I only have 20 minutes. I recorded another Lie algebra video yesterday, guys. You guys psyched about that? Should this just be a Lie algebra channel? Okay. Okay, so solve over the integers. Well, do we know this is solvable? Yeah, we know this is solvable because the GCD of 14 and 25 is equal to 1. And we know we can always write the GCD as a linear combination of the two guys. You generally learn that in an intro to proofs class. How do you solve this? You do it with the so-called extended Euclidean algorithm. Again, that's something that's generally done in an intro to proofs class. Let's review it here because it's important in an abstract algebra class, especially when you're looking at the group of units mod n. Okay, so let's do extended Euclidean algorithm with 14 and 25. So we'll start with 25 and use the division algorithm to write it, to write it with quotient and remainder with 14. So that's 14 times 1 plus 11. I almost wrote 9. Okay, and then what do we do from there? We take the old divisor and turn it into the new dividend, the old remainder and turn it into the new divisor. So this is going to be 14 equals 11 plus 3, and then you do the same thing again. So the old divisor, the new dividend, the remainder, the new divisor. So this is going to be 11 equals 3 times 3 plus 2. Then the old divisor, new dividend, old remainder, new divisor. 3 equals 1 times 2 plus 1. And so we get 1 in the end right here. And now you invert all of these equations. You might be saying to yourself, Self or Michael, that's my name, you could probably just guess and check a solution here, but it's good to know the strategy, sometimes. Although, if you know how to do the extended Euclidean algorithm, you should always spend a few minutes trying to guess the answer before you embark on the extended Euclidean algorithm because it's not very fun. Okay, now you solve each of these for the remainder. So we've got 1 equals 3 minus 2, and then we've got 2 equals 11 minus 3 times 3. Then you have 3 equals 14 minus 11. Then you have 11 equals 25 minus 14. And then you just push from the top to the bottom until you write 1 in terms of 25 and 14. So you start by taking this and pushing it down here. Okay, so let's see, what's that going to give us? It's a lot to put me on the spot doing this in real time because it's so easy to make a mistake. So here you get 3 is equal to 14 minus 25 minus 14. So that's equal to 2 times 14 minus 25. And you might say, well, hey, 2 times 14 is 28. That being said, you want to keep 14 and 25 as almost like variables here. Okay, so now what are we going to do from there? Now we can take this expression for 11 and this expression for 3 and plug it into this equation right here. So that means we've got 2 is equal to 11, but notice 11 is 25 minus 14, and then minus 3 times 3. You have to be careful about which 3 is the coefficient and which 3 is like the remainder. So we get 3 times 2 times 14 minus 25. And now you like consider 25 and 14 as variables and you like group them. If I were like, to be honest, if I were like recording this, I would take the time to color code everything and then just like cut it fast in the end, but you know, we won't do that. So here we're thinking about this 25 and this 25 as being like to be put together in that 14 and 14. Okay, so what's our coefficient of 25? We have 25 minus 3 times negative 25, so that's going to be 2 times 25. And then we've got negative 14 minus 6 times 14, so what's that? What's that? Negative 14 minus 6 times 14? Feels wrong.
Negative 14 minus 6 would be negative 7 14s, right? Or do you want to multiply it?
Minus 7 times 14?
Yeah, that's what it would be.
Is that right? Oh, this should be 4.
25s are wrong. That should be a 4. Yeah, you just...
There we go.
At the same time, yeah.
Okay. And now we can finish it off because we've got an expression for 2, we have an expression for 3. So that means we have 1 is 3 minus 2, but 3 is this, 2 times 14 minus 25, minus 2 is this, 4 times 25 minus 7 times 14. So what do we get in the end? What's our coefficient of 14? 9. 9 times 14. And then what's our coefficient of 5? Negative 6? No, negative 5. Negative 5 times 25. So we get something like that. Okay. So here, let's write that up here, and then we'll like kind of answer the question, what's the point? Which is something you do like kind of right after this in abstract algebra class. So we have 9 times 14 minus 5 times 25 equals 1. Okay, so now let's reduce mod 14, and notice that tells us that negative 5 times 25 is congruent to 1 mod 14. So that gives us like a modular inverse, you know, with respect to 14. Obviously 25 is like bigger than 14, so you probably wouldn't work this out mod 14 at the beginning. You would really like work mod 25. That's more motivating in this case. So if we work mod 25, notice that this term cancels and we get 9 times 14 is congruent to 1 mod 25. So that means that 9 and 14 are what they're called multiplicative modular inverses mod 25. So that's why you would want to do something like this. Okay. I've like given a problem on a test where the first problem is this, and the second problem is like...
Oh, we got $1 to push us up to...
Okay. And the second problem is like find 14 inverse mod 25. And like everyone got the first one right and no one got the second one right, even though like you just did all the work. All right. Let's do this one. So, suppose f goes from a to b. It's a function, and let's say w and x are subsets of A, and let's say y and z, international viewers out there, are subsets of B. Okay, so let's prove a couple of things. Let's first show that the image of W intersected with X is a subset of the image of X intersected with the image of W. You get equality when F is injective or surjective. I forget, but probably in the proof we'll figure that out. Okay, so how can we do this? Well, just look back to how you prove that you have a subset relationship, and you do that by tracing elements. So let's get some other names here. So let's say we want to show that C is a subset of D, you take X in C, and then you unpack what it means to be in C, and you should end up with X is in D. Really, there's like an unpacking and a repacking here. So that's exactly what we'll see as we work through this. It's just our C has to do with this function and our D has to do with this function. And then let's also not use X because it's the image of our function, and generally we'd like to use another letter for that. Let's use Y. So let's suppose that Y is in the image of X intersect W. Okay, but what does that mean? That means that there exists an X in W intersect X such that F of little x equals Y. That's just the entry fee into being inside the image. Okay, but that means that X is in W and X is in X by the definition of the intersection. Okay, but that means that F of X is in F of W and F of X is in F of X. Like by the definition of the image, just like applying the F to both sides, essentially. But remember that F of X was equal to Y, so that means that Y is in F of W and Y is in F of X. But putting that together, we see that Y is in F of W intersect F of X. So we get something like that. Okay. And then let's see. Let's start to prove the reverse and see what we need. See if we need surjectivity or injectivity. Maybe I'm sure people have already commented, but
I don't think so yet.
I don't remember.
They commented on your flip though.
About how great it was?
Yes, of course.
Okay. So let's suppose that Y is in F X intersect F W. So this means that Y is in F X and Y is in F W. But that means that Y equals F of little x for X in big X, and Y equals F of little w for W in big W. Now what we'd like is for those to be the same, but those are not the same unless we have injectivity. So if injective, then we have F of X equals F of W, which implies X equals W, which implies X is in X intersect W. Because little x is in X and little w is in W, but if they're the same, they're in the intersection. But now, applying F to both sides, we get Y equals F of X is inside of F of X intersect W. So in other words, you get the reverse direction only when this thing is injective. And it's if and only if this thing is injective. You can give an example where you don't have injectivity and you don't get the reverse direction. I would just use the function f of x equals x squared. Or maybe use some real cheesy one where like you take a 2-element set to a 1-element set or something like that. That would be even cheesier. Okay. That's probably what you should do, is just whenever you're like looking for counterexamples, just like look for the cheesiest example. Kind of like teaches you a lot about finding the whatever. Okay, so let's now prove a similar statement. So we have the same setup with the functions. Let's prove f inverse of y intersect z equals f inverse y intersect f inverse z. And now, like, I really abuse notation. This isn't really f inverse. This is like the pre-image. So it turns out the pre-image is like better behaved than the image. You get these equalities all of the time. Okay, so let's see how to do this. So proof. So we have to do double inclusion here, right? Because we're trying to show these two things are equal. Maybe we'll only do one. We'll see kind of how it goes. So let's suppose that x is in f inverse y intersect z. What does it mean to be in the pre-image? That means that if you apply f to this, then you're inside y intersect z. So that tells us that f of x is inside y intersect z. Again, we're unpacking this inclusion, or not, sorry, this element of thing here. Okay, but that tells us that f of x is in y and f of x is in z. But then, again, using the definition of pre-image, that means x is in f inverse of y and x is in f inverse of z. The definition of the pre-image. But that means that x is in f inverse y intersect f inverse z by the definition of the intersection. But then looking carefully at this, you'll see that everything here is an if and only if statement. Like, this is the definition of intersection. This is the definition of pre-image. This is the definition of intersection. This is the definition of pre-image. So everything here is an if and only if statement, which means we're done. Like, we did it all at once. Okay. Real analysis, last class. Is that okay? I think it's okay for this to be like 3.5 hours long and not like 1,000,000 hours long, right?
Yeah, I agree.
Will you guys forgive me?
They'll never forgive you.
Also, I mean, I don't want to like think too highly about myself, but I think like there's like a trip cord down here. I think that I really believe that being able to do these problems right before you go into the class, like reviewing these for a day before you go into the class, will kind of make you a rock star at the class. Yeah, anyway.
Let's get real.
Real analysis. All right, so what are some important things? Important. So Reed College in Portland, Oregon, their Calculus 1 class is essentially real analysis because they're so intense with their math program. I've applied there 4 times for a job. It would be my dream come true. So anyway, induction. Well, you might say, Michael, we just did induction. We just did induction for abstract algebra. That being said, the induction for real analysis is slightly different because a lot of things in real analysis you do with inequalities and stuff. Okay, induction, precise definition of a limit. Precise definition of limit. Now you might say, Michael.
You right?
Again, I've got this tripcord down here. Actually, it's the cord into the camera. That's what it is. So you might say precise definition of a limit, like you learn that in real analysis. You don't need to know that before real analysis. You know, maybe that's true, but often like you do precise definition of a limit in calculus. It's like a real hard day in calculus where everyone's kind of scared. Or I think the new thing is to do basic analysis proofs like this inside of an intro to proofs class. I started doing it last year. The new version of intro to proofs does like epsilon n and epsilon delta proofs for like a day. I think it's something to know how to do a little bit of before getting into real analysis. Okay. Basics of sets and functions. So sets and functions. We just did something with functions. We'll do some with sets as well in a kind of a more analysis type setup. And then maybe inequalities. Okay. So let's look at some examples. So, like, I don't know if you guys have noticed, I put this goal to make, like, 100,000 subscribers by the end of the year, but Justin thinks that's possible. I look at the growth curve, and I'm not so sure. But I don't know, like, maybe prove me wrong. We're going to keep saying it, because it's funny. Okay, so let's do this one first. Let's prove that 1 plus quarter plus ninth plus up to 1 over n squared is less than or equal to 2 minus 1 over n. So this is an induction argument, but like I said, it's not the type of induction argument that you would use in abstract algebra. It's more one that you would use in analysis. And that's because it involves an inequality. Okay, so how would you do this? You do it the same way. You got to do base case, you got to do induction hypothesis. Before we do that, let's note what's going on here. If we take the limit as n goes to infinity, so n goes to infinity, what do we get? We get the sum as n goes from 1 to infinity of 1 over n squared on the left-hand side. Then on the right-hand side, we get that's less than or equal to the number 2. In other words, we prove the convergence of the reciprocal of squares. Of course, like, if you're on Math YouTube, you probably know what the sum of the reciprocals of the squares is. It's the famous Basel problem, pi squared over 6. But you know, like a typical student in a class, you know, maybe not know that. That's why we got to get everyone watching Math YouTube, so everyone's like really familiar with these really beautiful results. Anyway, let's prove this. So let's do a base case first. So base case. So our base case will be the n equals 1 case. So for the n equals 1 case, the left-hand side is very simple. It's just 1 over 1 squared. So we get 1 is less than 2 minus 1 over 1. Less than or equal to, I should say. But that's clearly true because 1 is equal to 1. Okay, we're good to go there. Now let's make an induction hypothesis. So induction hypothesis. So let's suppose for some k bigger than or equal to 1, 1 plus quarter plus up to 1 over k squared is less than or equal to 2 minus 1 over k. Okay, that's our induction hypothesis. Now we look at the next case. So now let's consider, like I said, the next case, which is 1 plus quarter plus all the way down to 1 over k plus 1 squared, but I'll put the 1 over k squared in there to motivate us to use the induction hypothesis. So let's think about this being grouped. We can apply the induction hypothesis to that to give us this is less than or equal to 2 minus 1 over k plus 1 over k plus 1 quantity squared. Now let's like play some games until we get it to the right form. So this is going to be equal to 2, and then k plus 1 squared over k times k plus 1 squared plus k over k times k plus 1 squared. What did I do there? I just found a common denominator for these two things. Okay, so that's going to give us 2 minus, let's see, that's going to be k squared plus 2k plus 1 over this denominator, so k times k plus 1 squared. And then let's factor a minus sign out of this, and that's going to turn this plus into a minus. So we have really, this is minus k. So that's going to be k squared plus k plus 1. So it's going to end up with something like that. Okay. So now what can we do from here? What can we do from here? So this is going to be this is going to be less than or equal to 2 minus k times k plus 1 over k times k plus 1 quantity squared. So what I did is I just removed this 1 here, but since it's attached to a minus sign, I created something larger. But now, this k cancels with this k, this squared cancels with this k plus 1, and we have 2 minus 1 over k plus 1, which is exactly what we needed in order to finish the induction step. Okay, so now let's do a couple problems with sets. Okay, so let's show that a set minus b intersect c equals a set minus b intersect a set minus c. Okay. So again, it's to prove that two sets are the same, so we need to do double containment. So let's suppose that we've got an x in the left-hand side, so it's a set minus b intersect c. So what does that tell us? That means that x is in A, and x is not in B intersect C. So we get something like that. But what does that tell us? That tells us that x is in A, and x is not in B, or x is not in C. That's how you're not inside of the intersection. Right, so you have something like that. But, oh yeah, did I make a mistake here? Yeah, this should have been flipped over. Okay. But now we can just rewrite this. This is x is in A, and x is not in B, or x is in A, and x is not in C. Okay? But now we can put these together. And this is the same thing as saying that x is in A minus B, or x is in A minus C, but that means that x is in A minus B union A minus C. And then, to be honest, like, all of these are if and only if statements. So you would write this down exactly in reverse to get the other direction. Okay, let's do another one with sets. Okay, so let's show that the intersection from n equals 1 to infinity of 3 minus 1 over n, the closed interval 3 minus 1 over n, 5 plus 1 over n equals the open interval 3 to 5. Wait. No, sorry, this should be something else. Forget I wrote that down. Let's say the union, as n goes from 1 to infinity, of the closed interval from 3 plus 1 over n to 5 minus 1 over n is equal to the open interval 3 to 5. That's what I meant. Okay, let's get a little picture of what's going on here. So let's say here is 3, and here is 5. So let's see, the first one is going to be 3 plus 1 over n. So 3 plus 1, which is 4, 5 minus 1. So the first set is just this number 4. And then the second set will be 3 plus a half. So that'll be everything from here, and then 5 minus a half. So it's this thing right here. So the green is the second set. So the pink is the first set, the green is the second set. Then the third set will be 3 plus a third. So that'll be like from here, 5 minus a third, it's to here. So notice that we're growing until we take over the whole interval, but I'm claiming that we don't get the whole interval. Okay, good. So we need to do this by double inclusion again, but this is like not going to be an if and only if statement like the others were. There's like a little bit more going on here. You have to use like important principles. So let's suppose that x is in the union as n goes from 1 to infinity of the closed interval 3 plus 1 over n, 5 minus 1 over n. Okay, so that means there exists some natural number n such that x is in 3 plus 1 over capital N, 5 minus 1 over capital N. That's the definition of being inside of the union of indexed sets, that you're at least in one of them. But notice that this is a subset of the open interval 3 to 5. So that ends up with x is in the open interval 3 to 5. Okay, but that proves, here I'll just like do it quickly like this. That proves this direction of inclusion. So this union thing is a subset of 3 to 5. Okay, now let's do the opposite inclusion. So let's suppose that x is in the open interval from 3 to 5. Now this is tricky. Let's look at a picture here to get an idea of what's going on. So let's put 3 here. Let's put 5 here. And they're open, so that doesn't include those endpoints, everything in the middle. Now x is just somebody here. It could be closer to 3, it could be closer to 5, it could be equidistant from each. We don't know. So let's maybe take the smallest measurement between x and 3 and x and 5. And let's call that epsilon. So this will be epsilon. So in our picture, that's the distance between x and 3, but it could be the distance between x and 5. How do we encode that in there? We can encode that by taking a minimum. So let's set epsilon equal to the minimum of the distance between x and 3. So that'll be x minus 3. You might say, well, how do I know it's x minus 3 and not 3 minus x? Well, that's because x is bigger than 3 by the fact that it's in the open interval 3 to 5, and 5 minus x. Okay, so let's just note that x minus 3 is this thing which is epsilon, but 5 minus x would be this longer distance here. So taking the minimum takes kind of the appropriate measurement. Okay, so now let's take that and then find an n, which is a natural number, such that 1 over n is less than epsilon. So this is possible by the so-called Archimedean principle. No matter how small epsilon is, you can find 1 over n that's less than it. Really, you're finding an n which is greater than 1 over epsilon, but it's like kind of the same thing. Okay, so what's that picture look like? Now we look at the distance here. So this point right here, this would be 3 minus 1 over n. And let's look at this point right here, which is, sorry, 3 plus 1 over n. This is 5 minus 1 over n. So that 1 over n is less than epsilon, which means if we jump 1 over n from 3, we're before x. So if we shade this in yellow, if we shade this in yellow like this, we notice that we have gobbled up x. So maybe notice that x is in, let's see, 3 plus 1 over n, 5 minus 1 over n by our construction there. But that's going to be a subset of the whole union thing, just kind of by definition of subset and how a union is constructed. But that gives us the other inclusion. So I'll just put box. So we just proved this inclusion, the reverse inclusion. So by those two inclusions that we approved, these two sets are the same. Okay, good. Now, let's do like just a couple more. Okay, so like I said, it's useful to know about epsilon delta proofs and epsilon n proofs before real analysis. And like I also said, like in kind of modern intro to proofs classes, they're often taught doing that. And so let's do a couple of those. So let's show that the limit as x goes to 1 of 5x minus 3 is equal to 2. Okay. So the strategy I like to do for these is to do some scratch work to build my delta that'll depend on my epsilon and then write the real proof in reverse. Okay. So let's have our scratch work over here and recall that our goal will be that the absolute value of 5x minus 3 minus 2 is less than epsilon. In an arbitrary function, that's like f of x minus L is less than epsilon. Okay. Then we can do some manipulation. That's 5x minus 5 is less than epsilon, which is the same thing as the absolute value of x minus 1 is less than epsilon over 5. But this x minus 1 is related to this where we're sending x. So over here in our general world, that would look like absolute value of x minus a is less than something to do with epsilon, which we'll call delta. So that gives us our choice for our delta. And now that we've done this simple calculation, we can write it in reverse. So let's do that. So proof, so given epsilon bigger than 0, let's take delta to be equal to epsilon over 5 and observe that if x minus 1 is less than delta, which is equal to epsilon over 5, then absolute value 5x minus 5 is less than epsilon just by multiplying by 5, which is the same thing as saying the absolute value of 5x minus 3 minus another 2 is less than epsilon, which is all that needs to be done here. Okay. Let's do another one. Okay, let's do the limit as x goes to 3 of x squared equals 9. Okay, so again, we're going to do our typical strategy of scratch work and then writing it in reverse. So our goal will be to have x squared minus 9 less than epsilon. So we write the goal here, and then we work towards kind of the beginning setup, which is like this delta kind of thing over here. So let's see, this is like screaming out for us to do a factorization of a difference of squares. So we can have this as x minus 3 times absolute value of x plus 3 is less than delta. But now this x minus 3 is the term that we really want to get by itself, but we'd like to get it by itself not in terms of x. It's got to be just in terms of epsilon. And this is how you, and the standard way to do this is to do it with like an initial choice of delta. So let's notice if delta equals 1, then when x minus 3 is less than 1, then what do we have? We have x is between something and something. So it's between -2 and 4. Sorry, that should be in absolute values. Yeah. Then 3 minus. Yeah. So we have something like that. But now adding 3 everywhere here gives us 1 is less than x plus 3, which is less than 7. So that means x plus 3 is less than 7. So that means we have x minus 3 times x plus 3 is less than 7 times x minus 3, which if we want that to be less than epsilon, then x minus 3 should be less than epsilon over 7. Okay, so that sets up kind of our scratch work. Now let's go the forward direction. Okay, so given epsilon bigger than 0, let's take delta to be equal to the minimum of 1 and epsilon over 7. 1 because of this business right here, epsilon over 7 because of that over there. Now let's start our first observation with, now if the absolute value of x minus 3 is less than delta, then that means that the absolute value of x minus 3 is less than 1, because delta is less than or equal to 1, but that means that x is between -2 and 4 by like exactly what we did over there, but that means that x plus 3 is between 7 and 1. Okay, but that means that the absolute value of x plus 3 is less than 7. Okay, but now we see that the absolute value of x squared minus 9 is going to be less than the absolute value of x minus 3 times the absolute value of x plus 3. The absolute value of x minus 3 is less than delta, but delta is less than or equal to epsilon over 7, so this is less than epsilon over 7 times 7 because of that right there, but that's equal to epsilon. So we've got x squared minus 9 is less than epsilon, which is exactly what we needed for this limit to be what it says it is. Okay, let's do one more. Okay, let's maybe show that the limit as n goes to infinity of 2n minus 1 over 3n plus 1 equals 2 over 3 using epsilon n definition. Okay, so again, we're going to do like scratch work and then forward direction just like we did before. Okay, so let's see. Our goal is for the absolute value of 2n minus 1 over 3n plus 1 minus 2 over 3 to be less than epsilon. Right, and what we want is n to be large enough for that to occur. So how would we do this? Well, probably we want to like find a common denominator to put those together. So this is going to be 2n minus 1 times 3 minus 2 times 3n plus 1 all over 3 times 3n plus 1 absolute value less than epsilon. So I just found a common denominator there, no big deal. So let's see. This is going to be 6n minus 1 minus, 6n minus 3 minus 6n minus 2. So the 6n's cancel, and the minus 3 and the minus 2 add up to minus 5, but it's an absolute value, so it's 5. So really we have the absolute value of 5 over 9n plus 3. But since n is a natural number, that's always positive. We can kill the absolute value. So we have this is less than epsilon. Okay, so something like that. Then, what do we need to do now? So now let's note that 5 over 9n is... Ooh. So now let's notice that 5 over 9n plus 3 is less than 5 over 9n, right? Which itself is less than 1 over n. And so if we can show that 1 over n is less than epsilon, or if we can find an n so that 1 over n is less than epsilon, then we're good to go. This is a stronger n than you actually need because we've got this 5 over 9 here. But we don't need to find the minimum n, we just need to find some n based off the precise definition for the limit to exist. Okay, so now we're ready. So given epsilon bigger than 0, find a natural number n such that n is bigger than 1 over epsilon. And so let's just point out that this is possible by the Archimedean principle. The Archimedean principle says that for any real number, there's a natural number larger than that real number. So it's just the real number here is this 1 over epsilon. Okay. So now, notice that 1 over n is less than epsilon, but also 5 over 9n plus 3 is less than 1 over... Well, actually, let's back up for just a second. That was sloppy. So now, let's take an arbitrary little n bigger than or equal to capital N, and then note that 1 over little n is less than or equal to 1 over capital N, which is less than epsilon, and also the absolute value of 2n minus 1 over 3n plus 1 minus 2 over 3 is equal to 5 over 9n plus 3 by the calculation over there, which is less than 1 over little n by the argument that we made over there on that side, which is less than or equal to 1 over capital N by our choice of little n, which is less than 1 over epsilon by our choice of capital N. But notice we've got element of a sequence here, the limit of the sequence here, and then over here it's all less than epsilon, which is exactly what we needed in order to prove this limit fact right here. Is there a more efficient way? Yeah, there's a way more efficient way, but the first couple days you're going to be using the definition, so you kind of have to do the gnarly part. Okay, I think that's all I have unless anyone wants to do anything else.
Good stuff.
We done?
You still got 124 people in chat.
124 people in chat.
That's low for what you've had.
I know, look at the chart's going down.
I've been streaming for a long time. Plus, you know, most people like came by early and left.
Yeah.
Nothing in chat, but there's a delay, so
Yeah.
give it a minute. I made an ending graphic, but I don't think I was able to scale it properly, so we'll see what happens. When
Maybe put in chat and say like, I think we're all done. Any questions or anything?
Oh, do you have epsilon or 1 over epsilon instead of epsilon at the end? That makes the argument not make sense. Because epsilon's really small and...
Cool.
All good, all good. Any suggestion of resources where I can get IMO level geometry?
I haven't checked out this book, but there's a geometry and math Olympiads book that it was written by this guy. I forgot his name. I think he's like kind of famous in the math competition world. He streams on Twitch sometimes, and he doesn't have any viewers. Everyone should go watch this like former IMO medalist stream on Twitch. He's like live solving math Olympiad problems. It's amazing. He's a grad student at MIT now.
Somebody said, what is the greatest skill to be resilient in mathematical pursuits?
Maybe like
Perseverance? Like
yeah,
how big?
perseverance and like maybe making sure you know like all of the important facts and definitions for, you know, if you're in a class and you're given a homework set for a class, then you just covered something in the class, and you should be really familiar with all of the results from what you just covered in the class and all of the definitions from what you just covered in the class. I see like people all the time just like trying the homework, but then like not knowing definitions that we just did in class. Like, yeah. I know that people who watch math YouTube are probably not as likely to make those sort of mistakes.
Yeah, I guess.
But even good students make those mistakes all the time.
I think we're good. I don't see anybody that... They're talking about the math, but they're asking questions.
Cool. Classic math person.
I think we're good. Right?
All right, we got to shut this thing down then.
Yeah, I guess we gotta shut it down. Alrighty, I'll see if I can get my end graphic to display. See if it's not gonna be in the top left corner.
Oh, maybe one more story time.
Okay.
In case anyone has any contacts out there. I have this dream, it's a very big dream, where somehow I become the person on YouTube that gives little math lessons to other YouTubers. Because I think it would be funny. Most things I do in life because I think they would be funny. So I reached out to my favorite Star Wars YouTubers, Star Wars Explained, and they never emailed me back. Does anyone out there know them? I want to teach them some math. I even found a species in the Star Wars universe that's good at math that we could talk about. Anyway, that's my thing. Does anyone know anyone random out there that I could do a collab with? End of stream.
End of stream now. Yeah, just give them that to think on. Alright, cool. You want me to actually cut it?
Yeah.
Okay.